Yeah, we get to make one more jump. We had single integrals, we had double integrals, now we have triple integrals. We're going to find out what those things mean, And we're going to do it by looking at what single integrals meant, what double integrals meant, and making a jump. You see, every time we have an integral, we can think of it two different ways. When we had a single integral, and sometimes you don't really quite get a lot of this in Calc 1, but this is what integrals mean in Calc 1. One idea is area under f of x. That's one idea. That's typically what we think of an integral as, area under a curve between 2 points. Now that you understand the concept. Antiderivative gives us that, no problem. But the point is, this is a 2D concept. That's a 2D idea. The area on a plane is a 2D idea. However, we know that along the x-axis, that's an R1, that's a 1D integration. We're only going along one axis. Does that make sense? That's only along one axis. But there was another way to think about what integrals meant, what they mean. If I have a single integral, yeah, it can represent the area under f of x, a 2D concept. But it can also represent the mass of a straight wire, not a curved wire. We do that in Calc 3, right? But a straight wire. If you have a straight wire, you can find the mass of that straight wire given a mass density function with an integral. Well, think about that. If I have a straight wire, is that really a 2D concept? No. I mean a really thin straight wire, like something on the x-axis or right above it, or diagonal fine, but a straight wire. That's a 1D concept. Well, and then we went and we did double integrals. And in these double integrals, this dA stood for dx dy or dy dx, but the point is you're now integrating across two axes. You were integrating along the x and along the y. That gave us over a region. Is this ringing a bell for you? Yes. Well, that's a 2D integration, so in R2. And this also had two connotations. From the 14.2 and 14.3 stuff, we learned that a double integral, what that represents, that is the volume under f of x over that two-dimensional region. And now that you understand the concept, but it was volume. It was volume over 2D. That was a 3D concept. But in 14.4, we had a different take on it. We had this take on it. We said, well, wait. In 14.4, we learned something else. We learned that a double integral can also represent the mass of a really thin, and when I say thin, I mean like the calculus version of thin, like negligible thickness, like it's not measurable, like it's super thin. Does that make sense? We also learned that. We said, okay, double integral can also represent the mass of a really thin plate. Well, if we have a plate that's really, really, really thin, is that truly a 3D concept? Calculus-wise, really thin means negligible, infinitesimally thin. That means that we just have the region itself. That's a 2D concept. So let's kind of flesh this out and see what triple integrals are going to mean for us. So let's think about this. Are you guys okay that for a single integral, yeah, it represents area, but it could also represent mass of a 1D creature, a 1D creation there? And know that you're okay with that one. Okay, double integrals. Yeah, it could represent volume, 3D, or it could represent mass of something that's 2D. Do you see how it's bringing it down a dimension? Do you guys see the point? Double integrals could be a 2D idea for area or a 1D idea for mass. Double integrals could be a 3D idea for volume or a 2D idea for mass. If this is a mass density function. if f of x is a mass density function of the wire, so imagine a straight wire. not curved, straight wire. And this function tells you where the mass is along that wire. You guys getting the idea? The integral will tell you the mass of the wire. If f of xy is a mass density function of that plate, really thin plate, over a region, if it's telling you where the mass is located on that plate, then the double integral over that region of that mass density function will tell you the mass of that really thin plate. Are you guys getting the picture of that? That was that 14.4 idea. Now, let's look at what a triple integral could give us. Firstly, what's dv? If this is dA, it was across two axes, and this is dx across just one axis, what's dv gonna, what's that gonna give us? It's gonna give us all three, the x, the y, and the z. But the point is that those are ordered triples. Those things are across all three axes right there. You're plugging in ordered triples. Does that make sense to you? Okay, so keeping with this logic here, well, we have to go over a region. But now that region here, the region was one-dimensional, man, it was along the x-axis. Here the region's two-dimensional, it's along the xy plane. Here the region is what dimensional? Three-dimensional. It's got to go over some region in R3, some region in 3D. We call that region typically T, to distinguish it from R. R would be a region in 2D, T would be this region in 3D, or R3. Show of hands if you're okay with that one. Well, the triple integral can still give us two things. Just like this integral can give us area, just like this double integral can give us volume, this triple integral could give us a measurement, but here's the problem. If this area is in 2D and this volume is in 3D, this measurement of region is going to be in 4D. So it could give us some measurement of this thing, this region under f of xyz, but it's a 4D concept. So it could give us that. So number one thing, this could give us, can't quite call it volume because volume has a connotation of 3D, but it would give us some measurement of the region under f of xyz. But the point is that that would be a 4D concept, and that is super hard to imagine. Well, that's one option. By the way, we don't in this class, we're not going to jump down and just go straight for integrals. We don't do that. We learn what these things are before we start them. So I need you to actually understand this. Do you understand that this could equal area, 2D concept? This could equal volume, 3D concept. This could equal some measurement under the function over a 3D region, but it would be a 4D concept. Head nod that you understand the idea. Now, that's super hard to imagine. So let's consider it the other way. If an integral could equal the mass of a straight wire, a double integral could equal the mass of a thin plate. That's a 2D idea. That's a 1D idea. Then this could also equal a mass idea. Do you guys get where I'm going with this thing? This could equal the mass of a, well, now wait a second. A super thin straight wire, that's 1D. A super thin plate, that's 2D. What would that be?
Mass of a plane.
Mass of a, this would be a plane. A super thin. A mass of a plate with thickness, surface. That's what we're finding. Mass of a surface. Does that make sense? I'm going to call it mass of a plate with thickness, so you have this idea of a 3D region. But the main point is this. If this is mass of a plate with thickness, mass of a region, what D is it? Is it 1D? Is it 2D? Is it 3D? Is it 4D? What is it? 3D. It's 3D. So basically, this triple integral can represent the mass of a 3D thing. That's kind of cool. So it's something that's like more real for us, rather than imagining volume under a 4D surface. You're like, I don't even know what that means. Well, if we have a triple integral, we'd also represent the mass of a plate with thickness, that's some sort of region, and that's a 3D concept. But it only works if f of xyz represents what? This only represented the mass of a straight wire if f of xy was a mass density function. This only represented mass of a thin plate if f of xy was a mass density function, telling us the mass at any point along that thin plate. Does that make sense to you? This can only represent mass of a plate with thickness or a region, that's a 3D concept, if f of xy is a what? Notice what it says. Look. At any point in 3 space, that's why we have that R3. At any point, f would tell us the mass of that 3D shape in space. Anywhere along that 3D concept. Does that make sense? If I do the triple integral, it's basically adding up all the masses. That's what that's doing. So this works if that function is a mass density function. I'd love to just pause right there because we're about to just get through the rest of our notes and go right into examples as fast as I can because I want to make it real for you. I want to show you more how to do it than just explanation. I want to get right to it. It's honestly not that horrible of an idea if you understand single integrals and double integrals, triples. It's just one more step. But I do want to make sure you get the concept. Sometimes we as teachers think y'all understand everything and we jump right into what triple integrals do and not what triple integrals represent. And that's a bad way to do math. So I want to make sure that you fully understand this before we go any further, okay? So let's go through it like a 20-second, 30-second recap, and then we'll continue. Integrals can represent one of two things. They can represent a volume area idea, or they can represent a mass idea. Every time you jump down to a mass idea, you lose a dimension. So with single integrals, area is 2D, mass is 1D. For double integrals, volume is 3D, the mass would be a 2D idea. For triple integrals, the volume, the measurement's a 4D, the mass is 3D. Mass of 3D things make sense. It actually makes more sense than mass of 2D things. You ever seen a plate without any thickness? Neither. Now we can use it to find like charge densities and things like that, so it is very useful. But if we're talking about mass itself, mass typically comes in 3 dimensions, doesn't it? So what this says is, hey, the mass along this straight line would give us mass at every point in 1D. The mass along this thin plate would give us mass at every point along 2D. This says the mass density function would give us mass at every point, but now it's 3D, and it would add them all up and find the mass of the region in 3D. This is typically how we think of triple integrals. This is really, really hard to think about. The measurement of some 4D region under f of xyz, we can't call it volume. It's a dimension beyond volume. It's super hard to think about. Does that make sense? You can blow up a balloon in 3 dimensions and see the expansion of volume. Can you blow up a balloon in 4 dimensions? Well, it's hard to visualize that. So instead we say, yeah, you know what? We're going to consider this function to be a mass density function. And so what are we going to be doing? What are we going to be doing with triple integrals? What are they going to represent for us? What do they represent?
Mass. Volume.
Not volume. That would be double integrals. That's a volume idea for here. Volume under the function is 3D, or mass of thin plate. So we're going to think of this as a mass idea. But what mass is it finding? Look carefully. I need you to get it. This is the mass of the thin plate, right? How is the thin plate defined? The thin plate is defined along that region, over that region. Look at this. This is the mass of a straight wire. How's the straight wire defined? It's defined as a distance along the x-axis. Along the x-axis. Just over a region. Over a 3-dimensional region. So what this is finding is going to be the mass of that region. So whatever that region is defined as, that 3D region, this triple integral is going to find the mass of that region if this is giving us the mass density at every single point of that region. I know it's a weird concept, but you guys get the concept. Are you sure? Do you understand the idea that this is really hard to describe, the 4D stuff? So we think of this as yeah, okay. If that's mass density, then what this does is says, hey, find the 3D thing that you got. Is it 3D? Of course it is. It's X, Y, Z. It's going to be in 3D. This region will be in 3D, just like that's in 2D, just like that is in 1D. Along the X, along X, Y, along X, Y, and Z. It has this shape to it, this three-dimensional shape to it, this region in 3D. We call it T. What we're doing is saying, if this describes the mass density at every point in that region, then we can find the mass of that region. That's how we think of triple integrals. Head nod if you understand the concept there. Are you sure? So what are we finding? Mass of whatever this region is, given that that gives us the mass density every single point. Are you guys clear on that one? Okay, so here's some notes. We're now going to make the transition from our double integrals to our triple integrals. I'm going to make the connections for you. So typically, for double integrals, our first step was to do what? We typically drew the region. In 3D, we're not going to be doing that so much because it's honestly a little easier than that. In 2D, or sorry, for our double integrals, our first step was to define the region between two curves. You remember doing that?
Yeah.
Some of you guys need to be looking up here, okay? We defined a region. We drew our y, we drew our x, and we said we're either going to go along the y first, or we're going to go along the x first. Remember that? But it was always between two functions, two curves. So for here, our first step was define r between two curves. Okay, well, now for triple integrals. It's really easy to do this because your region is always on a plane. Verify that. Verify that. If this is a plate, and we're finding the mass of that plate was a really thin plate. It was a 2D plate. You guys get that? It was on a region that was 2D. It's really easy to define because you can draw the region on a plane. Now we have a region that is in, what's T? Come on, what's T? Think T equals 3D. That's what that means. That region's in 3D. So now I'm still going to define the region between two somethings, but they can't be curves, because curves are a 2D concept for us. They're on a plane. Right now, I'm going to try to define T as being between two what? Right. Surfaces. You're right. So that's our first step here. So now our first step is to define T between two surfaces. You know, I hope that makes sense. I don't hope, I need that to make sense to you. I need you to get the concept that when we increase an integral, like 1 to 2 to 3, we're increasing a dimension, basically. So think about this. These numbers travel along an axis, just between two numbers. This travels between two curves, along two curves. This, therefore, if I increase that, it's no longer curves, it's now surfaces. So instead of going between two numbers, I went now between two curves on a region. Now I'm going between two surfaces somewhere in space. That's the idea. Do you guys see the extension of that concept? So, but there's a really nice thing about this. If you can do this, define T between two surfaces, that automatically deals with your first integral. How many do we have to deal with? 3. So if I take away one integral, if I deal with it this way, how many other integrals are left? A double integral. Hey, do you know how to do double integrals?
Yeah.
So if you can define your first integral properly between two surfaces, then you're left with a double integral. So this is literally just an extension of double integrals. Deal with your first three-dimensional region between two surfaces, and then your double integral basically takes care of itself. Does that make sense to you? It won't make full sense until we do some examples, but I'm going to show this to you. Right now I want to write some notes out, make sure you all understand it, okay? So, what this does, this lets you deal with your first inside integral first, and then have a double integral to calculate, just like before. This takes care of the first integral, and then it leaves a double integral over a different region, over R. There's only one issue that we are going to need to deal with. It's kind of a big issue, and you guys are going to have a lot of brain turning when you do this, but I want you to imagine this. Please listen here real carefully. Please listen. With our triple integrals, if I'm going from a surface to a surface, I can choose to do that in the x direction, or the y direction, or the z direction, which means the double integral that I get, the region doesn't always have to be on the xy plane. We like it to be, but the region that we're going to get after we deal with the 3D concept, we're left with a 2D concept. Does that make sense? Just like double integrals. When you dealt with the 2D concept, you were left with a 1D concept. Do you guys remember that? You take care of the between functions, and then you're just going along an axis. That's pretty easy. Here, you go between surface, then you're left with just going through a region. So we get this double integral again. Only the region that we get, it could be on the xy, it could be on the YZ, or it could be on the XZ. So it could be on any one of those planes. It depends on what you pick to go across first, whether you're doing X direction, Y direction, Z direction. I know I'm throwing everything at you right now. You're just going to have to wait till we do some examples, and I will show it to you. But I need to get the ideas in your head. You guys understand that I'm kind of front-loading this? I'm trying to build an advanced organizer for you so that when we get there, your schema aren't all screwed up. Okay? I need you to build these things in your head, that dimensions grow as integrals grow. That happens. I need you to build this in your head. That in 2D you went between curves, and in 3D you're first going to go between surfaces. You guys get those ideas? I'm going to fill up those spaces in your mind in just a little bit. Okay, so right now I'm building you an advanced organizer. The main thing though is that once I deal with the 3D concept, I'm left with a 2D concept just like I had before, only the region could be on any one of the 3 coordinate planes. So if you want it broken down into as simple as I can make it, we are left with 2 tasks. The task number 1, 2 tasks and 2 regions. The number 1 task, we need to deal with a region in R3. Two tasks, 2 regions. Number 1, you have to deal, trust me, you gotta listen to this. You gotta deal with the R3 region first. You have to go between surfaces first. So 2 tasks, 2 regions. One of them, you gotta, number 1, deal with a region in R3. That would be the one between surfaces. Number 2, after that, after you deal with this region in R3, and I'm going to show you exactly how to do it, you'll deal with a very specific 2-dimensional region on a coordinate plane. I don't want to go any further if you have any questions at all. It's too important for you guys to understand these concepts. So, do you understand the idea of area versus mass, volume versus mass, weird 4D volume versus mass? Head nod if you're okay with that. Do you understand the mass idea only works if the function is the mass density function? Hello, yes, no?
Yes.
And then it gives you the mass of whatever region we're integrating over. It gives you the mass of the distance from A to B. It gives you the mass of the thin plate over a 2D region. It gives you the mass of a 3D thick plate over a 3D region. Head nod if you're okay with that one. Main goals here: deal between curves for double integrals. Cool. Deal between surfaces for triple integrals, and then we have a region in 2D. That's the main goal. It's the main goal in life right now, right? Your goal in life, you want to write your 5-year plan? Well, this is like a 5-day plan. Your 5-day plan right now is figure out how to make your first distance, your first travel, your first along whatever you're going between two surfaces in 3D. That's our main goal. After that, a couple other notes here. Are there any questions on this one before we continue? I really want you to have it down. Are we okay with it? Yeah.
Will we be using convergence to spherical just like we were using convergence to polar for the double integrals? For
Will
the
we be
integrals?
using spherical coordinates and cylindrical coordinates? Maybe. But not now.
All right.
Eventually, I don't want to ruin the suspense. Yay! Then we get something called the Jacobian. Like, what? Yeah, I'll prove to you how spherical coordinates, and you remember the RD theta, and I kind of give you a sort of quasi-proof? I can prove that with like the Jacobian. We'll talk about it. It's so cool. The second note, so that's note number 1. Note number 2. Just like double integrals, did it matter the order in which you integrated? dx, dy, dy, dx, did it matter? It mattered as far as the integral's hardness is concerned, but would you get the same answer?
Yes.
Fubini's theorem says you can switch them. Here, same thing happens. Triple integrals. By the way, I do want you to know this. dV. Just like dA gave us an area, can you see that the dV is a volume concept in 3D? That's why we're getting the mass of the volume of that region. That's what we're getting there. If f of x, y, z is a mass density function. Just like double integrals, these things can be evaluated in any order. Only there are 3 factorial permutations. There's 6 ways you can do it, because there's 6 ways to order that triple integral. You could have x, y, z, or x, z, y, and 6 different ways to do that. Does it matter? Well, ultimately, no. Ultimately, no. But I will tell you, just like double integrals, certain ways, certain orderings are way easier. Does that make sense to you? Remember that with double integrals? Sometimes dx was impossible, dy was way easier, sometimes vice versa. So these can be ordered, evaluated in any order, just like doubles, but there's 6 permutations. Can be evaluated in any order. I'll leave it like that. It's just that some are going to be much easier than others. Now, let's talk about the most important thing I can get you to understand. This step. How to define your triple integral between surfaces first. If we are doing a triple integral, then we have to integrate across, well, let's see. Single integrals was 1 axis. Double integrals was x and y, that's 2 axes. Triple integrals are going to be x and y and z. That's 3 axes. We have choices that we can make. We can go along x first, then y, then z, or any one of 6 permutations to do that. Does that make sense? You have to pick one. So I'm going to show you in our examples how to pick the appropriate choice, but we're going to have 3 choices here. You can only pick one thing to go first. You can pick to travel along the x, well, let's be this way. You can pick to travel along the y, or you can pick to travel along the z. Head now that you understand that. And it's going to always go between 2 surfaces. So along the x between 2 surfaces, y between 2 surfaces, or z between 2 surfaces. Those are called x simple. Remember the simples that we talked about? X simple would be between two functions, surfaces, defined in terms of x equals y's and z's. Y simple would be between two functions y equals x's and z's. Z simple would be between two functions x's and y's. Does that make sense? So you have a choice to make whether you want to travel along the x-axis, x simple, y-axis, y simple, or z-axis, z simple first. We'll talk about each one of those. Let's make it x, y, z simple. Is it simple to do? Generally, yeah, it's not too bad. I'm going to show you how to make some good choices here. Let's talk about what z simple is first. Get an idea. This is going to be the most common one for us. We really do want z simple. I'll show you why. Here's what z simple means. What this means is that we're going to define our R3 region, our 3D region, RT. We're going to define our R3 region in terms of z equals some function that has just what other two variables? Come on, what other two variables? That's right. So this means that we're going to define our R3 region between two z equals functions. I hope you're taking good notes right now because this is going to be like an outline of how you do stuff, right? From right here, this is where we start. Here's the point though. This is a cool point. If you make z simple, if you do z first, look at the board. Stop what you're doing. Look at the board. If you do z first, this has to be z, dz first. You guys get that? Are you sure you get that? If you did this, you don't need to write it down. We'll do some examples to illustrate it. But if you did this, you'd have a triple integral, and your dz would come first. Does that make sense? Yeah. Well, check this out. If you do that integral, you're going to be left with a choice of dx, dy. That's dA. That's a double integral over a region on the xy plane. So if you choose z simple, your region will be on the xy plane. Does that make sense? The region for the double integral we're going to create is going to be on xy. That's why we like z simple. Because if you pick z simple, you're used to regions on the xy plane. You already know how to define them. You already know how to switch them into polar. Did I just say something? Anyway, going back. So if you can do z simple, your region R, the R, not the T, okay? The T's in 3D. You deal with the R3 concept first between two functions, hopefully z. If it's between z equals some crap here and z equals some other crap and you go between them, you've just dealt with your first integral. That's fantastic. You're left with a double integral over another region. What plane is that region going to be on? Whatever plane doesn't have that variable simple. So if you go along z simple, your region is on xy. Does that make sense? Now, that's a wonderful thing because you know all about, we spent 6 hours, I looked at the videos I added at the time, it's like 6.5 hours, 7 hours doing double integrals. Do you know that? It's a freaking long time, all right? So you hopefully know all about freaking double integrals. Why do you think we spent so much time doing double integrals? Because when you get triple integrals, you automatically get double integrals. You automatically get a region. You automatically get the same exact stuff. That's why I had to have you know it so incredibly well. I couldn't just skip over double integrals to get to triple because every triple integral automatically has a double integral in it. Do you guys get it? You had to know it. That's why we spent 7, 8 hours doing it. So that's number one. Try to pick z simple. It's not always going to work out, but it's the easiest and it's the most common for us. Let's do y simple. I'm sure you can draw some comparisons here. If this z simple defines the R3 region between two z equals functions, this is going to define the R3 region between two what?
What?
Y equals a function of what? Now wait a minute. If it's y equals, what other variables are going to be over here? Now, if I had to put this, after I deal with the R3 concept, I'm going to deal with a 2D region. What plane is that 2D region going to be on? This was on the XY for our region. This is going to be on the XZ for a region. Whatever variable you do simple, you eliminate the variable. That's the whole point. Then we deal with a region on another coordinate plane there. Why don't you write out your own notes while I erase this side? Are there any questions on this side of the board? Can you write out your own notes? See what X simple would do. If we want to do X simple, we would have X equals, what two variables would it be over here, please?
Y and Z.
Perfect. And so the region, once we dealt with the 3D concept, we have a 2D concept to deal with. That's why we get a double integral out of every single one of these triple integrals. What would it be on? Beautiful. So fans feel okay with the concept. Am I starting to flesh out the idea for you? You're starting to see double integrals at work in triple integrals. Okay. The fourth note, I'm not going to write it down, but it's just, it doesn't go without saying because I'm saying it. But it's redundant. Defining the region is the hardest part of any double or triple integral. Defining the region. You guys knew that from double integrals, right? They can get very difficult. Same thing here. They're not super difficult, but you have to know what you're doing, especially with the double integrals. So I'm going to show you how to do it. There's another variable floating around. We got to deal with that thing. Right now, what's going to happen is we're going to do two very, very quick examples where the triple integrals are already set up for you. I just wanted to get you used to seeing them for right now. Does that make sense? So really quick, I'll show you how they work. There's not going to be any surprises at all. And then we'll start setting them up from scratch. That's the hard part. What am I going to give you on a test? Setup ones or ones you have to set up? Yeah, it's really pointless for someone to give you an integral that's already set up on a test. It doesn't show that you know anything besides how to plug in numbers. That's not going to happen here. I think you guys are better than that. I think you actually know. Like, no, I'm not. I'm not better than that. I want to set up. Please, I'm begging. I'm not going to do that, man. I trust that you guys can learn this stuff really well. I know that you can. You did excellent on your last test. So that's what's going to happen. I'm going to show you how you actually set up triple integrals so that way you don't get lost in the hard stuff, okay? But first, we got to get used to them. So I bet you I could probably just give these two to you and have you do them. But we're going to do them together. We're going very fast through it. Yes? Oh.
Noise.
Okay, obviously, there's a lot more to write down. There's a lot more to keep track of. That's one of the big things right there, is keeping track of what's going on. So first, let's kind of look at this thing. Could I start reordering these things, these integrals? Answer is, yeah, it doesn't matter how you reorder them. Sometimes we get a lot easier integrals when we do reorder. Sometimes it's easiest the way they are. My advice to you is, if one's set up for you, try it first. Don't try to reorder it right off the bat. Just try it first and see if it works. You waste a lot of time reordering things that you don't have to. Make sense? So let's try it first. What variable would these numbers be in terms of?
Y.
Good. You see how they still have to match up? What variable for these ones?
Z.
And these? What's my first integral tell us to do? Respect to what variable?
Y.
So everything else is held constant. So this integral says, let's keep, and you can write out x equals, z equals, and y equals. If that helps you, like I showed you last time, you can do that. You can still do it. I don't care. For me, it's very helpful. I like doing that. But that's completely up to you. Maybe even just on one of them. Also, make sure you're only touching the correct variable when we're integrating here. So if I integrate this with respect to y, which it says do that first, we deal with the first inside integral first, it says that we're going to get this 1/3 x y cubed cosine z. Head nod that you're okay with that one. Yes, no.
Yes.
Now, what do we do immediately before we start doing the other integrals? What do we do?
Evaluate.
So we're going to evaluate it. What variable is getting evaluated? That's why we write this stuff. That's why we're doing this in order of y. I know y equals 0 to y equals 3. We plug in the 3 first. You can speed through these. However, my goal here is not to get you to show me as many steps as possible on triple integrals. My goal at the end of this lesson is to get you to set up triple integrals flawlessly. That's my goal. Okay, your integration techniques, you know those. There's no more for us. So here we get this 27 divided by 3. Looks like we get 9xy cubed. Sorry, 9x cosine z. The y equals 0, that's completely gone. It already looks a whole lot better. Still okay with it? And then we do have to keep this in order, though. It's got to always match up our variables. So z's has to go next. Hey, what's the integral of 9x cosine z? I'm sorry, negative or positive? Positive. You be careful. That's the most often mistake in probably Calc 3 when dealing with trig. As we do integral of cosine's negative sign because I love it. And you go, no, that's derivative. You're going opposite. Sine. And before we continue, before we do our last little integral here, sine of 0 is 0. Love it when that happens. Sine of pi over 2 is 1. So this gives us integral from 0 to 2. Oh, you know what? We went from 3D to 2D to, we went from triple, double, single. Works great. Man, we haven't had one like that in a long time. I love this class. Don't you love this class? Man? That's crazy. This is easy. I love that. What do you get? 18. What's it mean? What's it mean? Well, it depends. It's either the volume measurement under that verify 4D. 4D surface here. This is either the volume for 4D over that 3D region, which is extremely hard to think about, or if that's the mass density function, that tells you where the mass density are located on this 3D image. Notice this is 3D. This region, this T is 3D. This would be the mass of that 3D region if that is the mass density function. That's what that represents. That's typically how we think of it. Should you guys feel okay with that one? Okay, tell you what. I want you to start one more. Little more challenging, but it's honestly the same idea. Just something interesting happens there. Are there any questions on this one now? Okay, cool. I want you just to do the first step. That's all I want right now. Just the first step. And then we're going to run through the rest of it real quick. Maybe write out what the bounds of integration mean, what variables those are related to. That's the first thing I always do. I look and make sure that I have x's with x's, y's with y's, z's with z's, to make sure I'm not plugging in the wrong things to the wrong variables. The problem here with 3D is you have a lot of choices. 2D, it was easier because you know that you have only one option for your other variable. Here you get a couple. You gotta be careful. Hey, what's your first independent variable? What's the first thing you'd integrate with respect to? What is that?
Z.
Okay, that means that these first two numbers are Z numbers. And these next ones are... Oh, thanks for the help on that one, guys. Appreciate that. And Y. So when I look at my first integral, just this guy, I leave the rest alone. All I care about is this. That's it. So when we do that, we're still going to have this y from 0 to 4, x from 0 to 1. I'm just focused here. You can tell probably why they set this up as dz first, because the x would be impossible, the y would be nasty, and the z would be easy. Okay, well, I'll probably put the z, it doesn't matter where it goes, square root y e to the negative x squared, but I do get a z out of it. Head nod that you're okay on that one. Now, I evaluate. Before I do the dx dy, you have to change whatever variable you just evaluated. It's got to change to these other two. It has to do that. You can't have any more z's because we're not ever going to be able to plug them in for those again. So whatever you just integrated with respect to, that's what you evaluate for. That's why we put z equals, and that's why we put z equals down here as well. So you know you're only plugging in for that specific independent variable. And now that you understand that one. Okay, then we continue. By the way, did you make it that far on your own?
Yes.
So here we plug in x, we get x. Plug in 0, we get 0. You're just getting an added x in here, well, multiplied. Now, is it a problem that we're going to do dx next? X should be my next independent variable. And it's just a double integral. Is that going to be a problem? What would you use? Try the U sub. Go for it. I'm going to do it on the board as you're doing it, but I want you all to try it. I just got through telling my Calc 1 students that we do U subs and changing bounds on practically every single one of these. Have you noticed that? It happens an awful lot. Change your bounds. I tell them all the time, change your bounds. It makes your life easier so you don't forget anything later. Change your bounds. I want to pause you here real quick to make sure we're on the same page. If we pick u as negative x squared, which is the correct choice, we're going to get this negative 2x dx. You can substitute right from there if you'd like, that's fine. I always solve for du over the coefficient, that's the way I do it. Most of the time I'll solve even with the variable over there and cross stuff out. It just depends on the technique, I don't care. Here we go, okay, the x dx, this is going to get replaced with du over negative 2. Head nod that you're with me on that one. If you change bounds though, you have to make sure that where this x value is mapped remains in the same place. So if I map 1 to negative 1, negative 1's on the top. You can't just arbitrarily switch those every time you want. 0 got mapped to 0, that's still on the bottom. So if you feel okay with that one. Now there is a problem with this. What's the problem with that?
Negative 1 smaller than 0.
Yeah.
So if I switch them, what's going to happen?
Sign.
So here's what I'm going to do. Don't get lost. You blink, you're going to miss it. I'm going to switch these around, but I'm going to eliminate that sign. You guys see that? Yes, no? Switcheroo changes the sign. No?
Is it 2 on the square root of y together? Or
Does that answer your question? I love it when that happens. I love crossing stuff out. Okay, if you want to know the whole shebang, here's the whole shebang. You ready for it? Watch. That negative would get moved right there, and you have parentheses, just like that. Can you follow that? Look at the board, please. Stop what you're doing, look at the board. That negative that was here would move right there, not in front, right there. Are you clear? When I switch bounds of integration, it changes the sign of the integral. So if I have a negative integral with wrong bounds, if I switch the bounds, it becomes a positive with that integral. Does that make sense to you now? You basically have two wrongs making a right. That's the way the real world works anyway, right? Am I right?
Yes.
Not right. Wrong. But in this case it does. Two negatives make a positive, so we got that. From here, hey, I love that. What's the integral? So we have this guy now. Before we do the final integral with respect to y, everyone in class right now tell me what you must do. What must you do?
Plug in.
You gotta plug in for what? What variable would we plug in for? So here, we would get from what? Which means we have this integral from y equals 0 to y equals 4, and we'd have the square root of y. And in here we get something kind of awkward. We get 1 minus, notice where the 1 comes from. 0 gives you 1. 1 minus e to the negative 1. Or you could put 1 over e, it doesn't matter, whatever you want to do, but it's definitely dy. I would love to know if that makes sense to you. Can you follow that one? Now after that, is it possible to integrate that? This looks crazy, but you all tell me what that is. What is that? It's a constant, it's just a number. You can even pull this out front. So that's a square root of y, so we're going to get that 2/3 y to the 3/2 evaluated from 0 to 4, and then we'll multiply by that constant. Add 1, you get 3/2. Divide by the new exponent, you get 3/2, but 2/3. And then evaluate from 4 to 0. Plug in the 4, plug in the 0. The square root of 4 gives you 2 to the 3rd power is 8 times 2 is 16/3. And then we have that constant. It's nasty, but that's the answer. I know that was pretty quick, but I understand it's quick. I'm doing this quickly to not get you to repeat your knowledge of integrals, but just to get us down to the final answer and show you how all this stuff works. So here's our little recap. Do you feel confident about understanding what your first independent variable is? Do you feel confident about matching up this with these numbers all the time, yes or no? So when you set up your own integrals, you keep that in mind. You have to match those up. Order doesn't matter, but you got to match them up. You guys clear on that one? Did you catch the only reason we really worked this out is to catch the whole bounds shifting, bounds switching, and the sign change. That's a big deal. Did you guys catch that? Change your bounds. That helps a lot, so you don't have to redo in here, plug your stuff back in. And then keep in mind what we're integrating with respect to. If we still have du's, man, don't change y's yet. Don't plug in for y's yet. Do that at the very end. Whatever you have at the very end of your integral is the last thing you plug in for. Should fans feel okay? Just for real. Comments, questions at all? From here, do you feel like you know what to do? Okay. We're going to pause here and come back and do some real stuff, set up our own. Okay, so here we go. We're going to get to the real stuff. This is the big stuff. How to actually set up your triple integrals appropriately. The number one thing that I want you to get to know is how to set up an integral across the R3 region first. That's number one. So what we call that R3 simple. Now, this right here has nothing to do with your region. That is not what we're talking about. What we're talking about is how the region is defined over here. This is what we choose to go across first. And now that you understand what I'm talking about, that's the first thing we do. So we have to choose to go between two functions of z, two functions of y, or two functions of x. My advice to you is pick z simple if you can. Try to go across the z first. In this case, I want you to look at something. I got x and y and z all equal to 0. That's not telling me anything. I got this x plus y plus z equals 1. These are all four planes. But I can solve any of these for x or y or z and have a pretty easy time doing it. Does that make sense? If that's the case, if it doesn't matter, pick z simple. Try that. So we're going to do z simple. If you pick z simple, what has to happen is we're going to have z smashed between two functions. So I want you to take all the stuff that says z in it, if you're choosing z simple, and solve it for z. So for instance, I've already got one right here. I got z equals 0. That's pretty fantastic. That, hopefully, you understand, that's going to be our lower bound for z. Does that make sense? It's going to be 0. Hey, can you solve that for z? Yeah. Well, if I solve that for z, z equals 1 minus x minus y. This is what z simple means. Z simple means that we're defining this 3D region between two functions of z equals. Z equals 0 is the first one, and z equals 1 minus x minus y is the second one. And it's between those two functions. I don't know if you're okay with that. Are you sure? That's the biggest idea that can get you to understand. So we're going to hang on to that in the back of our head. We're going to keep this. That's a big deal. Now here's what this also means. If we chose z simple, that's going to let us take care of the first integral. Our first integral is basically done. I know what it's going to go across first. I'm going to have what? Dx, dy, dz. What's first? dz's first because I'm doing z simple first, and it's between two functions, z equals and z equals. So fans feel okay with that one. Also something else. If I did z simple, my r is going to be on what coordinate plane? Perfect. So this is always our first step. Do the R3 simple first, and then draw your region. Because you're going to get a region on some coordinate plane. Hopefully it's xy, but it doesn't have to be. It could be xz, yz, one of those coordinate planes. Now we're going to take, and all this information is going to get put on the xy plane. Let's draw this. Hey, make sure you label it too, because it's not always xy. If you chose y simple, it'd be xz. You gotta label this stuff. We have x, always the horizontal for us if we can, and then z. If it's not x, if you had like the yz, you'd put y horizontal. Z is always our vertical one, okay? It's never horizontal. So x horizontal, y horizontal, z is always the vertical. Make sense? X, y, we're kind of looking down at it. So let's graph them. Hey, can you graph x equals 0 on the xy plane?
Sorry.
What type of line does it give us?
Or Y.
That's it. It's right here. I don't even need that much. So we got that one. We also have y equals 0. Now, well, what's z equals 0? Is that somewhere on the xy plane?
It is. Straight up from
That is the xy plane. So that's just saying we're on the xy plane. Okay, that makes sense. Now, on the xy plane, notice something. Notice, if we're on the xy plane, z is in fact equal to 0. Does that make sense? That means that any function that has z's in it, replace the z with 0, and you'll be on that plane. That will give you the intersection of whatever this is with that plane. So hence feel okay with that concept. So x equals 0, great. Y equals 0, great. If we're on the xy plane, z is also equal to 0. That means that we get x plus y plus 0 equals 1. That's stemming from the x plus y plus z equals 1. But if we're on the xy plane, then z equals 0. If we're on the xy plane, z equals 0. And we get x plus y equals 1. Hey, everyone in class right now, what is x plus y equals 1? What does it give you? What's my two intercepts? Have you ever seen this before? Cover it up. If I cover up the y, x equals 1, cover up the x, y equals 1, those are my two intercepts. So that's the line x plus y equals 1. Now, this was the whole point. If you have picked R3 simple, X, Y, or Z, whatever, you're going to be left with a 2D region. It's good. Listen, if it's on a coordinate plane, it's got to be 2D. That's now a 2D region. Does it look familiar? Can you identify that region as a double integral? Because if you can, you're practically done. Head nod if you're with me. Now you've got a choice. You can, for your double integral, think back to double integral days, you can choose to go along the y first, dy, or along the x first, dx. Which do you want to choose? It doesn't matter, as long as you set it up. I don't care. It doesn't matter. I like going along the y first because I like y equals functions. Does that make sense? So I'm going to choose to go along this first. If I choose to go along this first, I need y. So for my r, I need y to be between two functions of y equals. The first one is y equals 0. I'm between one function, y equals 0. Do you guys see that? The second one, well, if this line is x plus y equals 1, what variable would you want to solve for if I'm going along the dy, the y-axis first? I want dy, y equals. Head nod if you're okay with that. You guys over here, yes or no? So, if I go along the dy, the y-axis, I'm going from y equals 0 to y equals 1 minus x. You can even see it. You can see what's the larger and what's the smaller function by drawing the region. That's why we practice so much of that. Now the last one. I also need my final variable. Hey, how about this? What does the final variable always have to be between?
Constants.
Has to. So make sure that happens. First one between functions R3. Second one between functions in R2. Last one between functions in R1. That's numbers. That's just numbers. So we went along the y first dy. The x comes second. Go between the largest constants that bind that region. What are they?
0 and 1.
Perfect. That's perfect. Ladies and gentlemen, this is the biggest idea. The biggest idea is getting the R3 simple first, and then drawing your region. Why? Because then you have a double integral after that. Have I explained this? I really need to explain this well enough. If not, I can do it again. But I want to make sure that I've explained it well enough for you guys to understand this setup. Show of hands if I have. You actually get it. That was like half of us. Guys over here in the back left, are you sure that you're okay with it? I don't want to leave you hanging. Are you all right or not? You sure? So yes.
So if you had like z equals 1, you would not cancel out the z in that first x plus y plus z equation. You would fill in with a 1 and then solve for x.
You'd have
plus
to, yeah, you'd find the level curve of those z functions.
Okay.
If you did that. Might have, if it was z equals 1, I might have chosen to go y simple or something. You can always make it different if it's not suiting you. You can always change it. They're in 6 different orderings if you want. So choose the R3 simple that's the easiest to deal with. Since these were all the same, I chose Z simple because I wanted R on the XY plane. Because that's nice. We're used to that. We're used to drawing XY plane. Make sense? So Z simple, yeah, I needed to go between 0 and solve for Z. Got it. R's got to be on the XY plane. XY plane has Z equals 0. Okay, so XY plane has Z equals 0. Draw the line, draw the line, draw the line. Everything that's on the coordinate plane that this is referencing, that this refers to for R, draw them all. It's going to create a region for you. You get to choose how you want to define that region. Go between 2 functions of y or between 2 functions of x. I went between 2 functions of y first, 0 and y equals. That's what that's giving us. Then we go between constants on the only axis you have left should be constants. X equals 0 to x equals 1. For real, you guys okay with it? Now this will always set up your triple integral. Here's how triple integrals always work. Okay, here's how you set them up. After you find the z simple, and you find the next 2d simple, and you find the 1d constants, triple integrals work this way. We put our function in the middle. We have dv, it's going to be dx, dy, dz, or any permutation of that. Here's what you do. Whatever you found for the R3 simple goes here. We call that maybe T simple as well. R3 simple or T simple. Then we do the 2D or the R2 simple. That would be for our region, so R simple. And then here is always constants. If you're not having your constants on your most outside integral, you're doing something wrong. That's got to be there. Now let's put it together. Do you guys think that you could put it together if I asked you to do it?
Yep.
Mm-hmm. Let's start with the inside. We always work inside out with these. So if I'm going to set this up, I want an integral that's the R3 simple first. Hey, what axis did we go along for the R3 simple, X, Y, or Z? That's why we write this stuff down. Write down everything I've written. Keep your work organized. It's too easy to get lost. So if I went along the Z first, Z simple, I should have D what first? And then we're going to match that up. So if I went DZ, I've got to have Z equals something and Z equals something. That's why I taught you that method to match up the DZ with the Z equals. That's why we did Z simple and between 2 Z equals functions. That's the whole plan here. What's the smallest Z function that we're going between? What is it? 2 what?
1 minus x.
Yeah, if you write that, it makes it pretty clear. It says we're going between Z equals 0 and this. Those are 2 functions in R3 between Z equals. Head nod if you're okay with that one. Now let's build our way out. I want left side only, you guys. According to my region, I went Z simple first, cool. According to this, did I go X simple or Y simple? What did I do? Y simple, because that's the one that's between 2 functions. The X would be the constants. So the next integral I do would be dx or dy. Perfect. That means, right-siders, you guys, I have to have y equals something and y equals something. What's going to go right here, please? So we write all this stuff down. Y must be between 0 and 1 minus x. Last one, I think you can handle it. D. Whatever this is, has to be constants. It's got to match up with your outside integral, inside out. It's going to go from where to where? 0. That's almost it. Almost. But that's the hard part. The hard part is the setup. This is a really basic integral, but I want to make sure that you actually get it. Do you understand the z first, then the y, then the x, and that's why we have in the order between the functions that we have them in? Show of hands if you do. Also, the stuff matches up still. This variable still matches this variable. And look at this. The remaining variables will be these two remaining variables. They have to be. Or else you're going to do it wrong. It won't work out for you. This variable matches up with the next one, and the only remaining variables here have to be the final variable. Do you remember doing that? Matching up what it's equal to what's next? What it's equal to what's next. That always has to work for us. We are missing one thing that's really common when we get going. We get all caught up in the region. We miss out this one major thing. What is it? Yeah, which is, well, that there. Tell you what, I gotta be honest with you here. You are going to be distributing like crazy in this section with some rectangular triple integrals. It's crazy because there's a lot of stuff that happens. I'm gonna basically fly through this to give you the outline of it, but I want to know, if I give this to you right now, if you could start it. What would you integrate with respect to first? And then you plug in for the z variable. Then you integrate with respect to, and you plug in for the y variable. Then you integrate with respect to x, and you plug in constants. Does that make sense? So here's the idea, really quick. We integrate with respect to z, we get a z. We plug in for z. Z equals 0, no problem. We distribute. We're now forced to integrate with respect to y. Don't jump to the x. You're now forced to integrate with respect to y. Do you guys see what I'm talking about? You have to do that. It's in that order. That's the way we set it up. You can't just switch them around now. Otherwise, you got to redefine your graph. Don't do that. I'm hoping you can follow down the basic integration with respect to y, and the fact that right now, I've got a whole bunch of y's, and I'm going to have to plug in this for all of them. Do you guys see that? So this is going to be x times 1 minus, unfortunately the y is 0, I love that, but I'm going to get this in all three of these places, and this one's got to be squared. Now what? It looks crazy, but do you see that that's Calc 1? It's actually a basic Calc 1. It's a lot of distribution and combined like terms, but it's no u subs. It's just a basic Calc 1 integral. For real, some of these integrals are really easy because sometimes you can't do them when they're super hard, and they take too long. So a lot of times the setup is hard, but the integration itself, tedious maybe, but not horrible. So here, you can distribute by yourself, you can trust me. I'm guessing that all of you are going to trust me. This all works down to this. Here's my question to you. Are you going to be okay if I just give you the answer to stuff like this? I don't really want to waste your time integrating. You know what this is going to be. You're going to add 1, divide by 4. You're going to add 1, divide by 3. You're going to add 1, divide by 2. You guys see the idea there? Are you sure? Yeah. Then you plug in 1, you plug in 0. I'd like you to do it to make sure you still, get this down. But the answer here is 1/24. Again, my goal is not to just reiterate how to do basic integrals. It's to do the setup and do the first few steps so you're learning this and then relying on your old knowledge to do this. I don't want to be the type of teacher who goes, well, you guys are supposed to know this, so from here, you're good. No, that's not quite true. But from here, yeah, I mean, you need to be good from here. Is that fair enough to ask you to be okay from here? Okay, so you integrate, plug in 1, plug in 0, subtract them, and you're golden. Okay, now that you're okay with it. Now, what is that? What is that? Depends. If that is the mass density function of this region that we have 3D region, if that's the mass density function of that region, we just found the mass of that region. Make sense? It doesn't have to do with that as far as the region is concerned. It has to do with that as far as the mass density is concerned. So fans, you understand the concept there. That's pretty cool. Now we're going to do a couple more. Honestly, as many as we have time. We're just, it's all about the practice of the setup. So let's get to it. So find the mass of the region T, where the region T is given by that thing. Y equals x cubed, y equals x, z equals 2x, and z equals 0. So notice, if you were to graph all that stuff, it is going to be in 3D. Do you guys see that that's going to be in 3D? You got a cylinder, you got a plane, you got another plane, and you got another plane. And when they all cross each other, you get this three-dimensional region. That's what we're dealing with here. And I'm telling you, the mass density of that region is given by 2z. And now if you understand the problem here, this is how your test is going to look. I'm going to say, I want you to find the mass of the region. This is what this looks like. What's your first step? Say that again.
R3 simple.
R3 simple. So we're going to choose, well, we got 3 variables to choose from. We can choose x simple, y simple, or z simple. Now what's the best choice? It's between 2 of them. You're either going to choose y simple or z simple. How do we know? Well, choose the ones where the variables are already solved for, so you have to do less work. So y simple, maybe. Z simple, maybe. 2 options. What am I going to pick? I'm going to pick z simple. It probably doesn't matter. But I'm going to pick z simple because I like to draw my regions on the xy plane because I'm used to it. I make less mistakes that way. Does that make sense? So even though we have 2 choices here, I'm going to pick z simple as often as I can, provided the integrals are still easy. So let's go ahead, let's set that up. Step 1 is R3 simple. So we're going to write that down. You're going to tell me what you're choosing right now. What are we choosing? R3 simple. What are we choosing? So write down Z simple. And let's go ahead. If we're choosing Z simple, then the first thing we do is we have to make sure that Z is bound between 2 functions of Z equals. So here, since we already got it equal to 2 functions, we're going to have Z between, well, let's look at it. That ain't got no Z's. That ain't got no Z's. That's got some Z's, and that's got some Z's. So what's the smallest value for Z that we have?
0.
Yeah. I do got to tell you, a lot of times textbooks do not tell you this, but oftentimes we try to restrict where these graphs are to the first quadrant of whatever coordinate plane you have. So typically that's the case here. Because when we start graphing this does go down to the third quadrant rather than just the first. But oftentimes we restrict it to the first quadrant. So if that's the case, then x is growing positive, and we have z between 0 and 2x. Is that clear enough for you? That's what that does. Now, if I chose z simple, we're practically done. Do you guys realize that we've already done this right now? We just got that. That's the hardest part, is getting that and then making a double integral. Okay, let's make a double integral. How do we do it? Well, the next thing we do after we pick z simple is determine what? The region for our double integral. So let's talk about R, the region for our double integral. Can you please describe for me, and you should be writing this down every time you do these problems, what plane is the region for our double integral going to be on? That means that right now, you should be drawing me an XY plane. We always draw the, just like in double integrals, you always drew the region, unless you had like rectangular numbers and it was pretty easy, or if it was given to you. Here, we're always going to be drawing the region to set up our double integrals, because they're always going to be between functions. Now, oh my gosh, can you draw this stuff? Well, let's see. Do you need to draw z equals 0? Well, no, because that's literally the xy. Do you need to draw z equals 2x? It does give you something, though. It says that if z equals 0, then x equals 0. Do you see it? It's giving you the x equals 0 line. You can actually use that. So x equals 0, I know that that's part of my boundary, just the y-axis. Okay, can you draw y equals x on the xy plane? So use the pieces that are relevant. Let's draw that. What's that give you? Just diagonal line. What else can you draw? What else should you be drawing right now, right-siders? Can you draw that one? You can just sketch it. It's fine. This is why we normally consider the region to be here, because these are both traveling down on the third coordinate also. We're not going to consider that. We're just going to consider the positive. That z equals 0 also tells us that, so we want to consider that to be our bottom here. It's bound in the upper part of our graph. We typically do it, even if it's unsaid, we typically do that. I know it can be a little bit weird, but now, in order to do this really correctly, we need to outline what these functions are. I know this is y equals x. I know this is y equals x cubed. But you also need to know what the intersections are. Why do you need to know what the intersections are? Think about what you would do for your last most outside integral. It goes between what?
Constants.
Constants are the points. So you need to know what your intersections are so you can evaluate for your constants. Does that make sense? So how do we do it? How do you always find out where things intersect? You might do that. X cubed equals x, set these equal to find the intersection. X cubed minus x equals 0. We get x equals 0, x equals 1, and x equals negative 1. Now I'll tell you right now, the x equals negative 1. If I plug in negative 1, I get something that's outside of that region that we define. That's also how we tell that this was just in this quadrant and not in the bottom quadrant. Does that make sense to you? That would fail our constraint for our R3, how we define that. So this guy, no, that one not. But now I do know that x equals 0, and if I plug in 1, I know that's the point 1, 1. Listen, write these as points. That way, if you do go along the x first, and you go along the y second, or y first, x second, you have both values there. You don't have to just know along one axis. Does that make sense to you? So we're going 0, 0 to 1, 1, no matter whether we do x or y. Now, let's see if you're with me. Are you guys okay on the choice of z simple and 0 to 2x? Show of hands if you are. Perfect. Are you guys okay that the r is going to be on the xy plane? I know you're okay with graphing them. We've done that a lot for double integrals. I don't know if you're okay. Are you okay with graphing them? Yeah. You get okay on finding the intersection? Now, what right-siders would be the good choice to do next? We already went along the z. I'm going to have dz first. What's the next best choice? Would you go along the y or along the x? Given how we've written our, given that doesn't even matter, I can go along either one I want, but given how we've written our functions, what's the best thing to do? A dy or a dx? What do you think? Why?
Because it's already in terms of y.
That's yeah, that's exactly right. So let's do that. So I want to set up my region. I'm going to do dy first, which means I want to go along the y first. That means that y is the guy that we got to have between two functions. Now, use your region appropriately. What's the smaller, when I get to that, what's the smaller of the functions here?
X cubed.
And then I ultimately reach, yeah. Ladies and gentlemen, is that clear for you? I don't want to lose you now. You've learned too much for me to lose you now. Are you guys okay with that one?
Yes.
Question. Explain why we went along the y-axis. So the question was, why did we go along the y? Why did we do this? Why not that? The answer is,
We had to do the cube root of y.
say what now?
So we didn't have to convert it to cube root of y.
We would. If we went along this way, we'd have to have x equals functions. Does that make sense? Along the y, between y equals. Along the x, between x equals. Since these are already defined as y equals and y equals, that's the easier choice. Does it matter? No. No. But because it's already set up that way, it's nice to go along the y. Because now I'm between two functions of y equals. That's the point. That's why we did that. Is that clear enough? Now, the bottom, it's important you know the bottom and the top one. So along our region, along the y from smallest to largest, we first get into this region by hitting y equals x cubed, that's why it's small, and then ultimately by hitting y equals x, that's why it's a larger bound. So thanks for okay with that one. Hey, that set up the first of our double integrals. Now we set up the last part, it's the easiest part, it's always constants. Now we're going to go along the x. It should look very familiar because it's everything we've done in section 14.2 and 3. They're just double integrals and you practice the heck out of that. So I do need x to be bound between constants. What are the constants, please?
0.
It's why you write the point here so you know to go from point to point, but only along one final axis, 0 to 1. Show of hands if you understand the concept for that one. That's a big deal. I want you to try right now, take about 30 seconds, and I want you to set up the triple integral. Did you get to it? At least the setup? What's the first D, what should we have? Why? Why DZ? R simple? Was Z simple? Along the Z axis first between two functions of Z. Z simple. I hope you recognize the way that I taught you double integrals still stands. You do the setup first, then you worry about the functions. All about the setup. If I do Z, then I match up the variable here and here. Z equals, hey, what's the bottom? Yeah, that's why we write it this way. It makes it so nice. You go along the Z, that's where I'm going, along the Z. 0 to 2x. That's pretty painless. Then we go, okay, well, what's the next one I went along? That's where you look at your region. You don't have to draw a 3D region to do Z simple, or X simple, or R3 simple in general. You just got to know what variable you want to solve for. That's practically it. You do draw your R, and this gives you everything else you need to know for the double integral that we're left with. We went along what axis after the Z? So we went Z first, then we went along the, and we went, so along the Y. We went between two functions of Y. It's Y, we write them down. Y equals 2x. And lastly, the dotted line said we went along the x-axis. That's dx. That says we went from x equals 0 to x equals 1. Did you get the same setup? That's fantastic. That's, man, it's integration after this, which, yeah, you can screw it up, but honestly, that lends itself to a really successful test question. Well, if you complete one more thing. There's one thing that we've left out. Yeah, the mass density function. So don't forget that. That is one way you screw it up. Now, can you work on it? Why don't you try it? I'm going to put up a step about every 10 seconds and see if you can get the same thing. You know, I've been doing this a long time, but I still write y equals here sometimes, just to make sure I know I'm not messing with the wrong variable. I still do that. I still write it here just to make sure that I have everything in line. It's just good practice. It's good practice. Even though if you guys are really smart, you are really smart. If you know what you're doing, still write it. It's too easy to make mistakes here. That's an x, sorry. Did you make it that far with the 4x squared and the x minus x cubed? It's got to be that order. Did you get the x minus x cubed? What would your next step be? Keep on going. Did you get 1/3?
Yes.
What's it mean? What's it mean? It's the
Mass.
mass. Since this literally is the mass density function of this three-dimensional region, this thing with volume, this 3 space, the mass of this region is 1/3 whatever units. It's kind of cool, right? Kind of cool. Tell you what, we're going to do one more, and then we're going to call it good for today. I need to make this connection for you before we leave. I gotta have you know this. After that, you can probably do most of the homework. There's some other ones that we're going to practice with some just crazy setups, just so we can set them up. But as far as the idea of triple integrals, we're almost about through with triple integrals the way we do them. It's nice because they're very similar to double integrals. Just we need the R3 simple. So last one we're going to do, and then we'll stop for now. Come back and do some setups in a few more. So same question as before. but this is important. This is a good one. Man, I hope hope I haven't bored you enough that you are not paying attention any longer, because what this is going to do, this is going to make a connection for your next section. I'm gonna kind of prove, not really prove, but show you something here that should be really interesting. It's going to be so cool. You guys ready for it? Ready? I'm going to connect all of chapter 14 that we've done so far. It's all going to get connected. We're talking mass. We're talking, oh crap, that looks familiar. We're talking double integrals. We're talking how to switch these things. We're talking triple integrals. So the whole thing's going to come together in this problem, and then we're going to run with that. So number one, the first thing you do for any triple integral is what? Say all I heard was blah, blah, blah. I'm sorry, what now?
R3 simple.
R3 simple, yes. Let's do the R3 simple. Let's write that down. Write down R3 simple. Organization is pretty key here. Yeah, you don't want to get disorganized. You're going to lose some stuff. Don't lose your stuff. So R3 simple. What now? What would you choose? Would you choose to do Z simple, Y simple, X simple? What would you choose? Why? Why would you choose Y simple? Look at what it's solved for. That makes it so nice. If it's solved for two functions of Y already, man, choose Y simple. This is one of those cases where you wouldn't have Z simple, and it would not be logical to solve for it. Does that make sense? It'd be hard. So here, for sure, Y simple. Head nod if you're okay with that one. Now, what that means is that's our most inside integral. That means that we're going to have to get something Y between two functions. Are you guys okay with what I'm talking about? But what that means is you need to know what the bigger one is and what the smaller one is. Now, a lot of times it's really easy to see. If you have a 0, you're probably climbing. That makes sense. But if you don't have that 0, you might have to think intuitively, or you might have to wait for just half a second until you draw your R. I'm going to show you both ways. Intuitively speaking, that right there is a paraboloid. That paraboloid is traveling along the y-axis. Do you see it? Origin along the y-axis. If you learned anything about your surfaces, some of you, it's doing this. That's a plane. It's going like this until it hits the plane. That is the small one. For sure, I know that that's going to be x squared plus z squared and 4. If that works for you, awesome. If you're like, I don't know what that you just talked about, then you wait and you go, okay, well, you're not speaking my language. Here's the other language. That was Greek, and this is Roman. English. What are we speaking now? English. Use a translator. All right. If you have chosen y simple, where will the region for your double integral have to be on? What coordinate plane? So the r is going to be on the x, z plane. Right now, you should be drawing me the x, z plane. From what I told you earlier, if you have a z in it, it's always the vertical. X and y are always one of those is the horizontal, okay? So this is z, this is x. You're on the x, z plane. Does it make sense to you? Now, how about this? On the xz plane, y has a value of what?
4.
No, on the xz plane, on a coordinate plane, on the xz plane, y has a value of what?
0.
Okay. If I did that though, would that give you anything?
No.
This goes back to that one idea when you find your region. Do you remember that you do the intersection of your surfaces and it creates for you a level curve? Do you remember that? You go, hey, where do these things intersect? Well, these things intersect. We talked about it. That's a paraboloid doing this. That's a plane doing this. They will intersect. It's going to be a circle, and that circle has a projection as a level curve onto the xd plane. Does that make sense? So you don't just get to plug in 0 for this all the time. You do find where they intersect. You do find the level curve of where they intersect. That creates your region. It's just like any of the double integral. It says, hey, can you tell me where those two things intersect?
Yes.
Where?
When y is equals to
when they equal each other. Okay, well, at the intersection, we go, okay, then if y equals 4 and y equals x squared plus z squared, then 4 equals x squared plus z squared. If you want the common sense approach to doing this, eliminate the variable that you just solved for y simple. Just get rid of it. So solve somehow to eliminate that variable. You should be left with just x's and z's, or just whatever two variables you're on the coordinate plane. And now if you're okay with that one. So what we've done here, we set them equal. You go, hey, can you now graph this on your xz plane? Come on, people, help me out. What's that make on your xz plane? Circle. Radius of what? Centered at the. Think about the picture. I know even if you don't know the picture, you're like, I don't know the picture. You can still do it. Set them equal to each other. Set those equal to each other. It's going to give you this. You do need to know that's a circle. But that's a paraboloid. It's intersecting a plane. It's making a circle. That circle, listen, I want you to get the concept. That circle is out in space, but the projection of it, the level curve of it, is on the xz plane. That's the region. That's the idea of making a cylinder, subtracting big volume minus small volume. That's a double integral idea. That is what I want you to graph. Show of hands if you understand where that's coming from. So if you're not given specific numbers, planes, whatever, you do find the intersection, you draw an appropriate coordinate plane. If I do, then I got this nice little circle. It's probably the best circle I've ever drawn. It's on video too. I could draw circles. Woo! Love drawing circles when they work out good. Let me tell you about that professor I had. That one guy drew perfect circles. I ever told you that? Worst professor in the world. Uncannily bad at teaching anything besides freaking circles. I swear this guy could stand there and just go perfect circle. It's as if his arm moved independent from his body. Like, that's amazing. But you suck at teaching, sir. But his circles, mind-blowing, unbelievable. Taught physics. Why I know nothing about physics. Thanks, professor. Awesome. Professor Circle Sucker guy. Anyway, so that's the circle. Now wait. Now wait a second. So if that's the circle, this right here creates for you the region for your double integral. Does that make sense? This thing is above that region. Does that make sense? Here's how you determine what goes here and here if you can't picture it in your head. Are you listening? Take some point on the region. Give me a good point on the region.
0, 0.
Plug it in here and plug it in here and see which one's bigger. But it's got to be on the region. Do you get it? So you can kind of skip this whatever's in order-ness so far. Do your region first. So skip down, do your region first, and then go back to it. So if I don't know how to put them in order from here, then I find my level curve, I put it on the plane, my coordinate plane, just like we always do, and then you plug in a point. If I plug in 0, 0, y would equal what? And y would equal which one's bigger? Either way you do it, the 4 is the bigger y equals function. The x squared plus z squared is the smaller y equals function. Head nod if you're okay with that one. Hey, we're pretty much, we're getting there. We're pretty close. Now, wow. What type of region do you have here? What do you use for circular regions for double integrals? Don't shake your head. That's awesome. You trust me, you will not want to do this with a rectangular, because you'd have to go from here to here, that's across two functions, and then constants would be easy, but you would not want to do that. Trust the Leonard. Polar is your absolute best friend on this problem, because your region is a circle, and circles are really nice, but there's one thing you got to realize. Whatever coordinate plane that you're on, that is what determines your polar coordinates. So you are used to doing x squared plus y squared equals, I hope you're listening. You're used to doing x squared plus y squared equals r squared. Does that make sense? Now, listen, the reason why we draw these always in the same orientation, where x is horizontal and y is horizontal and z is vertical, is so that you always have the same type of idea. X is going to be your r cosine theta, but y is not going to be your r sine theta. What is? Z takes the place of y here. Does that make sense? Z takes the place of y, which means that it's not x squared plus y squared equals r squared, it's x squared plus z. Yes. So this looks a whole lot like polar. Yes. But x squared plus z squared equals r squared. Well, that's pretty darn nice, because now I can start translating this, since it's z squared. Hey, how much is all this stuff right here?
R squared.
So that would be r squared equals 4, r equals, how much, ladies and gentlemen?
2.
R equals 2. R equals 2. Yeah? Pretty neat. So from here to here, if you remember for double integrals, which one do we do first? Do we do the r first or the theta first?
R.
All the time. All the time. Which means that I want to start with r between two functions of r. And then I want theta between two functions of theta. So let's try to get this together. What's the small value for r? Think back to polar.
0.
Start the region immediately, 0. What's the large value? Wherever you hit your function is large value.
2.
I love constants. 2. If that had been like r cosine theta, you'd put r cosine theta. Now, how about the theta? That would be my last little piece here. What's the small value for theta? Where's it start? It's the full circle, normal circle, doesn't move too fast, too slow. We go around this way. 0 to what? Beautiful. That's perfect. So essentially what we're doing, I'm going to move over here because I want to take some space for this. Essentially what we've done, you don't need to write this down unless you want just really, really good notes. Here's what we've done. What we've taken is we've taken the normal idea of a triple integral over a region. And we said, you know what? No, let's think about this. Let's think about this as a first integral dy, and then another integral that's a double integral outside of it. But you can do that double integral however you want. So the first one, man, that's always between two functions, x, y, or z. Always, for us, unless we start talking about spherical. That's later. But it's always between two functions, x, y, or z. After that, you get a double integral. If you get a region that's circular, goodness, change that double integral into polar. Are you guys starting to see the connection between why we did polar and how that relates to this stuff? Inside one, you're always picking x, y, or z. But if I have a y or an x or a z, I'm left with any other two variables, xz, xy, yz. That creates a coordinate plane. That creates a region on a coordinate plane. That creates possibly a circular region on a coordinate plane. I can change that and go, well, let's consider my region to be same stuff inside, r dr d theta. Let's consider circular regions to be polar for that double integral. Does that make sense? I know we're learning a lot. There's a lot of stuff, and we're going to stop after this example because your brains are going to be fried after this one. But are you getting the connections? Do you feel like you've learned a lot today so far? Are you ready to put it together?
Yes.
It's not going to be that hard. There's just one more thing we got to do. There's one more thing. When we start setting this up, so here's our setup here. When we start setting this up, what's the first, what do we do? What simple, R3 simple do we do first? I'm going to need a I'm going to need that first. I'm going to need a dy first. Now, if I need the dy first, and I'm going to do r dr d theta. Do you see where that comes from? Here's our first integral, here's our double integral switching to polar. The problem is this. Look at the problem. I need you to look at the problem. The problem is, yes, I'm certainly going to have what variable equals what variable equals. I'm going to have y equals, and I'm going to have y equals. Does that make sense? I'm going to have that because I'm still integrating with respect to y first. Now that you understand the concept. That does not change. That's y simple first. I'm going between two functions of y. I'm going to integrate with respect to y. Just like we've said. Does that make sense? However, we also talked about this. Don't lose me here. Don't miss this thing. Whatever this equals, and whatever this equals, the way I've taught you, must match up to the next variables that you're doing. Does that make sense? They've got to be in terms of r. So when we look over here, I can't just put x squared plus z squared. I don't see no x's, and I don't see any z's over there either. Does that make sense? You got to change it. So let's change this. So if we're going to use polar for our region, we're going to change this now. But we already have the map. Hey, you tell me, how much is x squared plus z squared according to our polar region? What are we going to change it to?
R squared.
So r squared is less than or equal to y is less than or equal to, oh, be careful. Be very careful here. Is it still 4? No. It's 2. Do you see why it's 2? Wait, no.
Oops.
Okay. Well, I got thrown off. No, I'm sorry, I gotta repeat that. I heard him rattling around right back there, and I lost my train of thought, and I think I made a mistake. I'm not gonna erase the whole thing. I'm gonna erase this number, though. That's still 4. I'm sorry. The janitor came in and was like, crazy. Did he freak you out, too?
Yeah.
He's going to jump out again. He's going to get me. It's so fast. Look, I made a mistake there. I apologize. I want to catch my mistake here. That part is polar, but this is still a y equals function. I made a mistake. I started thinking the region, and I got confused myself. I started thinking the region that we're over here, and that's not what we're doing. What we're doing is we're going through 3 space between the paraboloid and between the plane, and we're just redefining the paraboloid in terms of something polar. That's what we're doing. I apologize for the confusion there if I confused you, but I want to make sure we're all clear on that. Don't change the 4. That's my bad. I got confused between the 3D idea and the region idea. Do you guys understand my confusion and get it straight here? So it's not 2, it's 4. My bad. So we're going to go, yes, along y simple. Just change the function in terms of r, so that way it matches up. But this is still r squared, and this is 4. It just, you cannot have this in terms of x's and z's if we have r's and thetas any longer. Hit not if you're okay with that one. For real, yes, no. Okay. Now let's wrap up the rest of it. I know the r dr d theta. Yes.
You can't just put in r is less than or equal to y, which is less than or equal to 2. Or you could do that.
You mean like square root all of
Yeah.
it? Because then you have square root of y. I don't want to do that. Now let's wrap the rest of it up. Now, as long as we've done r simple first, we did our y simple. Now we got this region that's polar. We have dr d theta. We always go along r first, and then we go along theta second. But we've already determined these things. R equals what to what for our polar region? From where to where?
0 to 0.
Beautiful. And then for our theta, we already got it. 0 to 2 pi. Head nod if you're okay with that. Yes, no, yes, yes, yes. Okay. Hopefully I didn't totally screw that up for you guys, so you understand that I made a mistake and that's supposed to be 4. Now, I'm gonna tell you something. Some books have it different. They're a little wrong. Please, even though some of you might want to, we're missing one thing. You know what that thing is. What are we missing? We're missing the mass density function. That mass density function is what? Please don't start changing that into like r sine, r cosine. Please don't change that. because that even if it was like X's and Z's, some books change it ahead of time, they shouldn't. Because if that has a variable like this, you have to integrate with respect to that variable. Don't worry, I got more. Does that make sense? I got lots more. So you leave this. Look, it's going to be fine. Even if that doesn't have y's in it and you integrate, you'd be able to change it later in the terms of these things. The only thing we got to make sure that we match up, y equals with y equals. Don't change this, but then what the y equals has to match up with the rest of your variables. Whatever this is has to match up with these things. So if it's really good with that one. Can you try to do the first step? Y simple, mass density, change to polar, so we got to change that to polar to match. We got, okay, r squared to 4, we got dr, r is matching between 0 and 2, that's what we got. Theta between 0 and 2 pi, that's what we got. Basic integration. Do you see how you have to leave that variable to integrate that? It's with respect to y. You need to leave those variables, because if you have any of that variable, it's got to have something to integrate. You're still going 0 to 2 pi, you're still going 0 to 2. Did you all get the 1/2 y squared? And then y goes from r squared to 4. Did you all make it that far? Which one do we plug in first, the 4 or the r squared? Okay. I think I get that. Did you get that? 8 minus 1/2 r squared? Oh, sorry, out of 4. Tell me what's the next thing you should be writing. The R. Do you remember how I told you the R is one of the easiest things to forget about? Have you forgotten it yet? Good for you, because I made such a big deal about it. Don't forget the R. I'll get mad at you. Yeah, well, you'll get mad at you, because you get to the end, you go, oh my gosh, I forgot the R. And it's just such a pain. But that R, R's got to be there. R, d theta. Any comments, questions about this whole thing? So R simple, the region. You feel confident doing the polar regions these days? Even if they're not x, y, you can do x, z, whatever. Just change the way you define your polar functions. Then we crush an integral. And we go, okay, well, this is theta equals 0 to 2 pi. 0 to 2 for our r. I know that's going to be 8r minus 1/2 r to the 5th dr d theta. Still so far so good. Yeah, no. Yes, no. Okay. So that is hopefully that looks like that. 4r squared minus 1/12 r to the 6th, and then we're going to plug in for I love it when that happens, when there's no other thetas or anything, and you just get all r's, and you plug in for r equals a number and 0, you're going to get left with a constant. That constant, if I've done my math right, is 32 over 3? I don't remember. I'll do it again. I'll do it again. That's 64 divided by 12. 2/3. Can you correct me if I have a mistake? Did you get the same thing?
Yeah.
Did you bust out your fraction button on your calculator? 48 minus 16 is 32. So we get 0 to 2 pi, 32 over 3. Yes, no. Did you make it that far?
Yeah.
What's your last step? Easy step. You know, easy step, but we make some mistakes on this. When you're integrating a constant d whatever, the whatever is important. It's telling what your variable is. So this needs to give you 32 over 3 what?
Theta. Yeah.
And that theta is being taken from 0 to 2 pi. So we're going to get out of this 64 pi over 3. What does it mean, please? That's the mass. That's the mass of the region that I wrote on the board earlier, depending on the fact that the mass density function of that region is given by rho xyz equals y. That's what that came from. Do you feel like this has been explained well enough that you guys completely understand the concept? Concept is big. Can you do all of it? What's your first step again?
R3.
R3 simple, and then you have a double integral with a region, and you define it however you learned in 14.2 and 14.3. We're going to stop here for today. We're going to come back next time. We'll honestly just deal with a lot of setup, setting the problems, because that's the biggest thing. We're going to skip a lot of this. It takes too long. So we're going to worry about setup next time. All right, so welcome back. A few more examples, and we're almost done with this idea. So we're going to focus on mostly setup, and I want to set this problem up. If you recall from the triple integrals, we had a couple ideas about what these things did. What they can do is give us some measurement of a volume idea under a 4D surface, which is kind of weird. Or if we have a mass density function for a region, what it will do, what these triple integrals will do, they'll find the mass of that region. And that's generally how we think about it. So the key here is setup. And I want to talk about this one. This is a very interesting problem. What we're going to do is we're going to set this up two different ways. Now we're going to look at the only two ways it really makes sense to do. If you remember, and I hope that I need you to remember, what's the first thing you do for a setup of a triple integral? What do you do first? Say it again. R3 simple. So we choose either x simple or y simple or z simple. What's the one we typically try to stay with? We try to, and that's an option for us here. Y simple is also an option for us here. X simple, not so much, and I'll explain why. Y simple and z simple will be okay, because I have a y equals 0 and a z equals 0. So y simple, z simple, that would be nice, because I have a 0 at the bottom, like that. X simple, I'd have to go between two functions of different variables. That would be a little bit awkward. So right now I'd put x simple off the table. I'd be focusing on y simple or z simple, and now that you understand what I'm talking about. So let's go ahead, we're gonna do z simple first, just the setup. And then we're going to do y simple, and we're going to see how the setup changes. So let's focus on the z simple. So number one thing in any triple integral, we always do an R3 simple first. Then we're left with a region that's on a coordinate plane. So R3 simple. Let's just try the z simple for now. If we're going to do z simple, then ultimately what we need to get out of it is z being mashed between two other functions. That's what we would need to get. So let's look at our functions. I've got, well, that doesn't have a z in it. That's got a z in it. That doesn't, that does. These are going to give us our two functions of z. Now that you understand what I'm talking about. What's the smaller one, do you think? 0. Generally, that's kind of a safe bet that 0 is going to be your bottom bound for any between two functions in R3 simple. We typically try to keep in the first octant. That's generally what happens, or at least above the xy plane. If that's not the case, if you don't know, the next step, and we did this last time, go down to your region, figure out your region, and plug in a point. That will always tell you what's the bigger function of z and what's a smaller. Does that make sense to you? We did it last time. So for right now, yeah, I'm pretty darn sure that z equals 0 is going to be our smaller of those two functions. What would I have to do to figure out the bigger of the two functions? What would that be? You can say it louder because I can't hear a darn word you're
Solve for
saying.
z and then plug in.
Okay, solve for z and the only other one that has it. So z would be, well, square root of what's in that square root?
4 minus x squared.
So for R3 simple, if we choose z simple, z's got to be matched between 0 and the square root of 4 minus x squared. Head nod that you're with me on that one. After the R3 simple, what's the next thing that we do? Come on, quickly. So our region, I always like to list out the plane that region's going to be on. So if I choose z simple, our region's got to be on what coordinate plane? It's always on the plane that doesn't include that variable. So if we have z simple, we're on xy for sure. So our region's going to be on the xy plane. That's great. Hey, what do you do for regions? Like every time that you're setting up, now that we've got the R3 simple, we're setting up a double integral. You do what? Every single time. What is it? Let's draw it. So when we draw our region, yeah, it's going to be on xy. Use all of these functions that actually make sense on the xy plane. So basically, anything that involves x's and y's, you can put on that plane. Z equals 0, well, not so much, because that says you're on the xy plane. X greater than 0, that we're going to use here in just a second. Y equals 0, that's relevant. What's y equals 0 give us?
Yes.
So I know that already we have got that line. We have x equals 2y, so we're going to draw that one. X equals 2y, since we have the x and the y variables, it's pretty easy to draw. Me personally, I love things in terms of y to graph them. So from x equals 2y, I'd probably think about it just 1/2 x. You go, well, we get that diagonal line. That's all that gives to us. Head nod that you're okay with that one. All right, so we got that on the xy plane. We got that y equals 0. We have this. We're going to definitely be above x, to the right of x equals 0. It could be that way. This gave us our diagonal line. Now, does that give us anything? Hey, if it has an x or a y in it, it's going to give us something in the xy plane. The key here is, though, on the xy plane, what's the value of z?
0.
So when you're on that coordinate plane, you need to zero out all of that R3 simple variable. So for us, we go, yeah, that's great. This is one of the lines. This right here, though, this is x squared plus z squared equals 4. But hey, folks, we're on the xy plane. Z is 0. And that gives us two other values. That gives us x equals positive or negative 2. Well, hey, what is that on the xy plane? What is x equals 2 and x equals negative 2? What's that? Yeah, those are our vertical lines. That's exactly right. Only there's one condition over here. If x equals plus or minus 2, I have a condition that's going to eliminate one of these. What's that condition? Yeah, so I don't care about the one over here. This guy, don't worry about it. X got to be positive. That's just giving me this vertical line at x equals 2. Show of hands feel okay with that so far? All right. Now, if you're the person who, man, you can't visualize that at all, I have no idea. Go down here first. Take any point on the inside of this region and plug it into both this and this, or this, and solve for z here, which I'd already done earlier. Plug in any point on this region and it will show you what the higher function is. Does that make sense to you? You can always come back and fill this in later if it's not intuitive for you. Fine. Do your region first, plug in a point to your z functions or your R3 simple variable functions, and it's going to tell you what's the bigger, what's the smaller. Show of hands if you understand that concept. Here we got kind of lucky. We got the 0. We know that's larger than 0. It's a square root. I mean, it's going to be there. This right here, we got our r on the xy plane, no problem. Anything involving x and y, we graph that. We let z equals 0, gives us some more lines up there, and that's our region. Now, what direction? So we know that for our triple integrals, R3 simple takes care of the inside, the most inside integral, and then we get this double integral over a region. That's our region. And you get to pick whether you want to go along the x direction or the y direction first. Can you tell me what an appropriate choice would be? Would you want to go along the x direction, dx first, or dy first? What would you do? Why? Why? Someone else besides you guys up here, why? Why would you not want to go dx first? Let's look. If I went this way, if I did this, I'd enter my region by hitting this function, which would easily be solved for x equals 2y, that's fine. And then I would end it by hitting 2. Doable? Very doable. And then along the y-axis, I go from 0 to 1, because this is the point 2, 1. Does that make sense to you? That'd be fine. However, I'm not going to choose that way. Here's why. Here's why. I always love, and it's nice because you have one function. Do you notice how we're not switching functions? You guys see what I'm talking about? That's great. But I wouldn't choose that way. The reason why I wouldn't choose that way, can you see it? Why? Why would I want to do this way first? dy first. Now, I'll tell you, it has to do with the lower function. What's the lower function? It's way easier to plug in zeros than it is another function. That's what, if I can do that and keep it between two functions and one of them 0, that's the better way to go. Does that make sense? Yeah or no?
Yes.
Okay, let's set this thing up. So we're finding the mass. Always do our setup first. Give yourself some room to do your setup. And we're going to end this thing with, well, R3 simple, and then our R2 simple, and then our constants. That's how we work it from the inside out. So what's the first thing? What was our R3 simple? Everybody, come on. R3 simple was? Oh, so we need D what first? Okay. So from right here, we got Z equals and Z equals. The R3 simple's always going to give it to you first. Everyone in class right now, what's my lower bound, please? What's my upper bound, please? Perfect. That looks great. Head nod if you're okay with that one. Now, if you want to go an extra step on here like I like to do, before I set up the rest of it, I like to give myself some other inequalities. If I'm going to go along the y first, so that'd be R2 simple. On our region, that's R2. I'm going between 0 and 1/2 x. And that also gives me something else. After I go between 0, function of y equals 0, and y equals 1/2 x, then I'm going to go across this region from 0, oops, from 0 to 2 along the x-axis. So same double integral setup that we've always had. Go along one axis, then go along the other. The first axis, we call that R2 simple. The second axis, that has to be between constants. Always, every time, without fail. Head down that you're okay with that one. All right, so hey, now we can do the whole setup. The next thing, so if I did this, if I did R3 simple, I now have dz because I chose z simple. The next one would be dx or dy. Everybody help me, come on. Because I chose to go through our two-dimensional region along the y-axis, and then we have to go from y equals, that's where inequalities come in. 0 to y equals 1/2 x. That's helpful, that's real nice. Drawing your inequalities automatically sets up your integrals from the inside out. Lastly, well, there's only one choice. I have to do dx. I know that my x's have to be constant. Sure enough, they are, from 0 to 2. And it looks pretty good to me. There's only one thing we're missing. What are we missing? Yeah, if we're going to find the mass, you got to have a mass density function, which means here we're going to have what? That's where I'm going to stop on this example. I want to see that you understand the setup. Do you understand the setup on the choice of z simple, where all of this junk comes from and how to get that triple integral? Show of hands if you do. That's pretty much everybody. That's good. What would your next step be? Integrate with respect to 1/2 z squared. You plug in 4z, you get this squared, just gives you that. Then with respect to y, plug in some stuff. Then with respect to x, plug in some stuff, and you find the mass of that region. Hey, that's okay. That's an option. It's not a bad option. Your answer here is 1. That's how fast I want you to do it. No, that's just the answer. Okay. Just look at it. 1. 1 and done. No. Now, there is another choice here. I said x simple is not a great one because x simple you'd be between two functions. I always love being between 0 and a function. If I had that choice, I'm going to make that choice every single time. But I want you to see y simple for one very simple reason. When we set up the integral, something special has to happen with it. So I want to show that to you. So let's say that you get to your test, you don't see z simple, even though it's kind of a nice setup, you see y simple. Let's try that. So instead of R3 z simple, we're going to do R3 y simple. If we do y simple, that means we're going through a 3D region, that's what we call R3 simple, 3D region along the y-axis. We have to intersect two functions where y equals something. So y is going to get mashed between two functions y equals. That's what we want out of this. One of them is really easy. Everybody right now, what's one of the functions y equals?
0.
That's why we picked that. That's why we're not doing x simple. So I know y equals 0 gives me that bottom bound of 0. Pretty much can take that for granted most of the time. The other one, well, that's not a y, that's not a y, doesn't have a y in it, but that one does. So if I can solve this, then that gives me my other function y, and I automatically have my inside integral set up. Instead of doing dz first, I'm going to do d, and I'm going to go from 0 to 1/2 x. Show of hands feel okay with that one. Okay, so if we went y simple on this, what's the region? On what plane? Come on, what plane? So for our r, we're going to have, yes, you're right, the xz plane. Every single time you have a double integral, you do what with the region?
Correct.
Let's draw that region. Let's do that. So everything that we have over here that involves whatever these two variables tell you is going to be graphed on this plane right now, on the xz plane. Hey, what axes go where? What's the horizontal one? What's the vertical one?
Z is vertical.
Z is...
Z is vertical, sorry.
You're forgiven. Don't let it happen again. It's messed up. Now, let's see what's relevant. Is y equals 0 relevant?
Yes.
How is it relevant?
Gives you.
It tells you you're on this plane. That's what y equals 0 said. Is x equals 2y relevant? Does it have one of these variables in it? Then it's relevant. Everything. But here's the deal. If x equals 2y and we're on the xz plane, it's very much like this, where z equals 0, we're on the xy plane. Now, what is going to equal 0 out of that? We're on the xz plane. What's going to equal 0? Then we get x equals 2 times 0 because we are on the xz plane. Y is going to equal 0 on the xz plane. You're going to get x equals 0. This one thing right there is going to lead you to a better answer. If you have x equals 0, it's going to stop you from going all the way around a circle, which we can't do here, and you're going to see that in a minute. So x equals 0 says, hey, we're stopping right here. This one would also do it, says x has to be greater than or equal to 0. Does that make sense? Most problems wouldn't give you that. I'm giving it to you so we don't have this other side to it. So that's one thing. We got this on the plane. This one's also got to be there. Z equals 0. What's z equals 0 going to tell you? Yeah, it's going to tell you that we don't go any further than this. We're trying to find the region bound between here and here. Basically, that's in this first quadrant. That one tells you I'm not just over here either. I'm only in the first quadrant. And not if you're okay with that one. Now we keep on going. That's also some. So we took care of this. That's saying we're positive of x equals 0. We have that's giving this horizontal line. This says we're on the plane. This says, hey, when y is 0, we have this x equals 0. Kind of redundant here, but that makes it to the right-hand side. And then we have that guy. Can you graph x squared plus z squared equals 4, yeah or no? What's it look like?
Circle.
Sure. Since that's on this plane, that's a circle centered at the radius of, for sure. However, this is why it's important that you draw these freaking things, okay? If you just draw the circle and go from r equals 0 to r equals 2, you're going to be absolutely fine. But if you go theta from 0 to 2 pi, you are not going to be fine. Do you see how this forces you to stop right there? And you don't get to come back because x is greater than 0. This says the region that's bound by z equals 0 and x equals 0 and this circle is just this quarter of a circle. Show of hands if you understand that concept. That's a big deal. That's why we draw these things. That's why we graph them every single time. So let's see if we can do the setup. I know that I got the y. Huh. Wait a minute. What I think I gave it away already, but what type of coordinates do we use for stuff that's like, circles and stuff? Polar. Let's use some polar coordinates here. So if we got circular regions, why not switch this to polar? If that's the case, then I want to be able to go from here through my region, from here to here first. What always comes first, theta or r?
R.
So I know that r is going to be between what and what, please? After that, we get theta. Here, again, why we draw the region, why we put everything up here on whatever coordinate plane we have is so that you get this stuff correct. The setup is the most important point. Where does it start? Where does it stop? What's theta do?
0 to pi over 2.
That's the key. Not pi, not 2 pi, just 0 to pi over 2. Are you with me? Okay, let's do the setup then. Triple integrals now for this. We're going to go what are we doing first? Are we doing y, dy, dx, or dz? So you need a dy. After that, well, that's just the R3 simple. After that, we just have a double integral. So this guy, you can put that in parentheses and deal with a double integral basically independent from that. All it did was give you a region. All we're doing is defining that region in terms of polar because we had a circle. So instead of having the dx, dz, what has to go over here for polar regions, everybody? What has to go there?
RD.
Beautiful. RD theta, okay, so I know that I want y equals here, y equals here. I want r equals here, r equals here. I want theta equals here and theta equals here because we always match up our integrals from the inside out with our variables. This one, if you've done the inequalities, you should be able to set it up. I want to see a proper setup. Go for it. I'm not going to give you long. We're all about setup. What goes here, please?
0.
What goes here? 1/2. What goes here, please?
0.
What goes here?
2.
Here?
0.
And
5.
that's the proper setup. We're missing one thing. What's the one thing? Whatever the mass density function is. So in our case, we had z. It's still the same z. Man, that's it. That's the whole setup. I want to know if it makes sense. If you can see this as being a correct setup and this as being a correct setup, I'm a happy guy. Can you see them both as correct setups? Are they going to give you the same answer?
Yes.
They have to. Fubini's theorem says they have to. I'm going to prove that to you. You get take my word that that's one, but I'll show you over here for one reason. Yes.
Do we need to switch the y equals 1/2 x into terms
Just
of
going to
r?
get to that. I promise. I'm going to right now. But thanks for asking. I mean, thanks. That's a great question. That's a perfect segue. Do you have to switch this stuff around? Listen carefully. This you will ultimately have to switch. Why? There ain't no x's. Right? You're going to have to switch that to r's thetas. Hey, what is x? X is you can switch it right now. Could you have to switch it right now? No, you don't. You can switch it later, but you will be switching it. Some books make you switch it right now. Some books make you wait till later. It depends on the textbook. You can do either way for me. I don't care. But understand the concept. That's a big deal. The way I've showed you, you should be switching that right now to r cosine theta. Does that make sense? You should be doing that because when you plug it in, you're going to have r cosine theta. This variable has to match this. The remaining variables have to match these things. That's got to be there. Are you guys clear on what I'm talking about? Now this one, listen, this one. Sometimes you can get away with changing that now, and sometimes you can't. My encouragement to you is integrate this first and then switch it when you have to. And the reason why I would say that is because if that had any y's in it at all, it probably won't. But if it did, and you just switched it right now, you wouldn't be able to integrate with respect to y. Does that make sense? So integrate this first, and then change this stuff around. Does that make sense? So I'm going to start switching things. You brought up a real good point. So let's change this. You go, well, x, no, I don't want the x. I want to make this 0 to pi over 2. I want to make this 0 to 2. I want to make this 0 to 1/2 r cosine theta, because x is on the horizontal, and that's r cosine theta for us. Z would be r sine theta. Is that clear? Not y. Z. Then I have z dy. We'll do that one first. And then I'm going to have an r dr d theta. Truly, do you understand the concept of what we just did, yes or no? Okay, so I'm going to go through it pretty fast. Hold on to your hats here. We're going to integrate this thing. I want to show you some things that you should be doing and not doing, okay? So first thing, 0 to pi over 2, no problem. We're just going to rewrite this double integral out here. Integrate with respect to y, we get z, y. We also are going from y equals 0 to 1/2 r cosine theta. And then after that, we're going to have an r dr d theta. Now, we're going to plug that in. Y equals this minus y equals that gives us just 1/2 r cosine theta. R dr d theta. This is the point I'm going to make right now, though. Where you do have to match these up to your next variables, and that's exactly what we did here. This z doesn't necessarily have to right away. Right away. In fact, I would encourage you not to, just in case you have that variable. Just in case you have to integrate with respect to that z. Does that make sense to you? Just hold on to it. But then, later on, when you get down to your evaluation, you get down here and you go, wait a minute, wait. All the rest of my junk has r's and thetas. All the rest of the stuff has r's and thetas. This z is a problem. That's where you must change it. You must change it at that point. You can't go any further than right here before changing all your variables into the rest of these things, r's and thetas. Does that make sense? So now we're going to go, well, how much is z? Z took the place of the y-axis. That's why we always write these in the same orientation. X and y, or x and z, or y and z. So we get the same relationships over and over again. This z now is going to be, well, can you figure it out? If x is r cosine theta for horizontal, y is r
Sine theta.
Wait a minute, r sine theta is y. That's y. Well, it is if we're on the xy plane. We're not. We're on the xz plane. That's why we get r sine theta out of that. So when we make that little transition, that z becomes this thing. I'm going to do all this at once. We got a 1/2. We're going to have an r, an r, and an r. That's r to the third power. We're also going to have a sine theta and a cosine theta. So we're going to get this 1/2 r cubed sine theta cosine theta. Well, we took care of the r, so it's just dr d theta. I really, really, really want to make sure that makes sense to you. That's a big deal. Where you change things and where you don't change things, in my opinion. Other books can do it different. Me personally, I always make sure these variables match up to these variables. That is a big deal. I don't change this right away. You could, in this example, you could, because this is not a y. So if you really know what you're doing, like, I'm going to change it now. Fine, as long as this function does not have to do with that variable right there. Is that clear for you? That's a huge deal. I cannot stress that enough. Me personally, I wait and then I change it when I have to. When I've done integrating all the certain variables I have, then I change it. You say that here, well, that's a z, there ain't no z's, okay? Then you're able to change it. But if you have a y and there's some y's, you can't change it there. You got to integrate first. Now, after this one, what would we do here? Integrate with respect to what? R first. Okay, so I'm going to write down here to get our R1. Sorry about changing sides of the board on you. So integrating with respect to r, we get this 1/8 r to the 4th. We're going to plug in for r 0 and 2. And then we're going to have this sine theta cosine theta d theta. Well, that looks friendly. 0 to pi over 2. If we plug in 2, we're going to get 16 over 8. That gives us 2. Plug in 0, we get 0. So we end up getting 2 sine theta cosine theta d theta. Yes, no? That's really friendly. That's really, you have options here. You could do what? That's what most people think. And that's fine. You can do it right now, get the correct answer. You could say, well, you know what? That looks an awful lot like this one identity that some of my trig teachers tried to get me to learn. And I never did, but it exists. Maybe you know it. That saves you some time, because then instead of a real use of, you have a trivial use of. And you go, well, this thing right here, that's well, what's the integral of sine?
Negative cosine.
Okay, negative cosine. And then this is the opposite of a chain rule. U sub is the opposite of chain rule. So instead of multiplying by 2, you divide by 2. So this would give you negative 1/2 cosine 2 theta. And theta is going from 0 to pi over 2. Which means we get negative 1/2. And we get this thing. We got cosine of pi minus cosine of 0. And we got negative 1/2 times negative 2. Negative times negatives are positive, we get 1. Same thing. You get the same thing either way. The key here was identifying what the correct setup is. After that, integration, pretty easy. Honestly, you guys are smart guys and girls. You know how to integrate. So I want to make sure that you guys are okay on the setup. Show of hands if you feel okay with the setup. Okay, we got one more. We switch gears for a little while, and then we're done with the section. So next one, kind of important, deals back with how you set up integrals across regions. Are there any questions at all before we continue? Are you sure it's sinking in? You're on your head. I want to make sure y'all are with me. Yeah? Okay. Okay. What I want to do, same type of question, I want to find the mass of the region, mass of the 3D region, where the mass density function is that one, and our 3D region is bound by these two curves. Listen, I'll give you just an overlying concept that fits for basically any part of calculus. If you ever have to find the whatever bound by two functions, you need to find the intersection of those functions. If you want to find the area between two curves, you set the curves equal to each other, you find the intersection. If you want to find the volume under a surface bound by two regions, you set the regions, well, you set the functions equal to each other, and you find this region. So when I'm not given stuff like, hey, x equals 0, y equals 0, some planes, some curves, some cylinders that define for you a real nice 3D region, the idea is going to be this. Can I have your attention here real quick? I know you're writing stuff down, but the idea is this. If I set these functions equal to each other, it's going to give me an intersection. That intersection is going to be a curve. The intersection of a 3D region is a level curve. Does that make sense? So what this is going to do when I set these equal to each other gives me some sort of curve. That curve gives me this cylinder that contains this volume. That's what's happening. It's giving me this thing that if I integrate across, it's going to have the volume inside of that level curve. It's like the outer bound for our 3D region here, our volume we're trying to find. Does that make sense? So find the intersection, gives us a level curve, integrate over that level curve. That is the region that 3D surface, 3D region is going to be hanging over. That's the idea here. Head nod if you're okay with that one. So now the first idea, set it equal to each other, but before we do that, you're going to pick right now whether you think we should be R3 simple in X direction, Y direction, or Z direction. This one should be kind of obvious. What is it? Y.
Because the y function is equal to y.
I mean, ¿por qué? Porque they're equal to y. They're literally equal to y. That's a really nice choice. So if you have two functions that are automatically equal to y, you're probably going to do y simple. Does that make sense? We try to do z simple all the time, but I mean, shoot, if they're just going to give it to you, I mean, take it. So this is going to for sure be y simple. Head nod if you understand why. Literally. Okay. So if we're going to be y simple, travel across a 3D region along the y-axis first, we have to mash y between two functions of y equals. Now, it's going to be up to you to either do this intuitively or hang on for a second to get the region. Me personally, I can do a lot of these intuitively because I watched section 11.6 and 7 and know how to do polar coordinates and graph. Okay, so I know what these surfaces look like. This surface, that's intersecting the origin. This one ain't. I'm going from, on the y-axis, something that intersects the origin, something that doesn't. That's going to be the smaller of these functions, and that's going to be the bigger. So right now, I know that this is going to be x squared plus z squared, and 8 minus x squared minus z squared. Well, wait a minute. I don't know how to do that. I'm not intuitive. I can't picture this. That's okay. That's okay. You just won't get this right now. You just wait a minute. You do the R, and we come back to it. Does that make sense? I'll show you that in just a second. The key right now is understanding why we are doing y simple. Do you understand why? Okay, every time we set up a triple integral, we do the inside integral across R3 simple. And then we have this double integral over a region on a coordinate plane. So let's set that up. If I did y simple left side only, what coordinate plane is our region going to be on? The XZ plane. Okay. Now what's the region? Listen. The region we talked about at the beginning. You shouldn't be working right now. I don't want you doing the wrong thing. The region, if you just put y equals 0 and you just put y equals 0, what you would find is where this intersects the y-axis at the origin. That's what you're going to find. You're going to find where this intersects the XZ plane at that whatever that circle is. Okay, that's what you'd find. That's not what we're looking for. What we're looking for is that level curve that contains, so that cylinder that going along the y-axis that contains the volume. So if ever you have the region bound by these things, bound by two curves, the first thing you do in Calc 1, set them equal to each other. First thing you do in Calc 3, set them equal to each other. Find the level curve, that will give you the region. If you set them equal to each other, the y's are gone. It will be on the xz plane. Does that make sense? So if you have region bound by, set the functions equal to each other and find the level curve. Why don't you try that right now? Set them equal to each other. That's all I wanted from you right now. Did you set the functions equal to each other? Right now we're finding that level curve that creates a cylinder that contains that 3D volume that we're trying to locate right now, the 3D region. By the way, you can do some fancy pants math on this stuff. Make sure that you're looking for the squares plus squares a lot, because if we're going to translate to polar, which that's really helpful. So do things like factor out the negative. Don't be afraid to view this as one piece. If I add this to both sides, I got one of them, I add another one, I got two of them now. So some algebra technique it really helps. Divide by 2. That's a really nice way to figure out what this region looks like. What's that region look like? Draw the circle. Is it a full circle? Yes, that intersection that's what's all matters. So what's nice about these regions that are bound between two functions, it typically gives us a nice level curve. So this level curve is a full-on circle. Draw the circle. Draw it on the xz plane where z is the vertical. It's got to be a circle centered at the origin with a radius of 2. And the region is the entire circle. Hey, since we're literally just dealing with a double integral now, and this is literally the only region we have to worry about, would you do this in terms of rectangular, or would you do this in terms of polar? Why? Why polar?
Circle.
So if it's a circle, and all we got to worry about is dr d theta. Let's define our r and let's define our theta. Let's do it right now. I've already got y between two functions. We'll talk about r between two functions, and we'll talk about theta between two constants. By the way, stop, pause. I need to make sure you see this at this point. If you don't have this right now, I don't know what this is. If that was you, you told me you were going to tell me. This is where you would find it. So you know that you're going to be between two functions of y because we have y equals. That's called y simple across the 3D space there. If you find your r on the xz plane, yes, set your functions equal. Find the intersection. That gives you that level curve that's going to contain, this thing's going to shoot out there, okay? It's going to shoot out there. It's going to contain the volume between those things. That's what it's going to do. That's why we find it. We integrate over this area, we find the volume of that. That's brilliant. But as soon as you find this region, if you were not able to intuitively tell me what's smaller and bigger, this is where you do it. So on the xz plane, find a point on the inside of your region. Give me a good point. Plug in 0, 0, if you can. Do that. So plug in something inside there, though. Not on the edge. Inside. Do it on the edge, you're going to be equal. Don't do that. Inside. So plug in 0, 0. If I plug in 0, 0 here, I get 0. If I plug in 0, 0 here, I get 8. Which one's bigger? Well, 8. That's telling you that is the larger of the function. So if you weren't able to find it at first, now you go, well, that gave me 0 for some point on the inside. That gave me 8 for some point on the inside of this region. I don't care about points outside. I care about just points inside, not on the region, just inside. Therefore, this is the smaller of these two functions. And that gives me the high one and the low one. That's the whole idea. Now, I'm going to go a little bit deeper on your understanding here, okay? Check this out. Do you remember when we found volume between two surfaces? You found the intersection. The intersection created the region. And then what I talked about was you're taking this cylinder out, you're intersecting a smaller function, and you're intersecting a larger function, and you're subtracting the volume, bottom from top. Do you remember doing that? The intersection is important for that reason. When you do your integral setup, do you recognize that that is going to be what you plug in on the top? That is what you're going to plug in on the bottom, and you subtract them. That's exactly what's happening. You're literally doing the same thing, but you find the intersection to give you that cylinder so that you can subtract those volumes. In this case, it's mass of the region, but that's the same idea. You guys get that idea? Okay, so now we're on it. Let's go ahead, let's start changing this. We know that if this is our circle, we can certainly change this into polar. It tells us that instead of going from 0 to a function of x and z, I now have, circle with x and z's, I now go from the origin to a radius of 2. That tells me that I'm going from 0. I'm going to start going a little quicker through here because I know we've done it many, many times. So I'm not going to be asking you for a lot of this, but if you're confused, you by all means stop me. So I know that polar function says I'm going through the region from 0, so I hit my region immediately, and then I end at r equals 2. I'm also going full circle on this thing. So that's 0 to 2 pi. Head nod if you're with me. Okay, so we start changing this. We start setting up our triple integral. So for a triple integral, I know that our mass, that's what we're finding here. Mass is going to start with the triple integral of our mass density function. We're going to do that in a minute. But I know that I'm going to do, what symbol did we do? I need to set up my first integral, and then I know that my region for my double integral is polar. So I need to set this up. If I could write it correctly. Basic integral, R3 simple, that's Y simple. Then I got a double integral. It was over a polar region, so I have a polar double integral after that. Should have understand the concept there. That's a big deal. Now, keep on going. This guy has to be y equals the small function to y equals the big function. Are you listening? You still have your attention? Do you remember over here how we had a little snafu? We had this 1/2 x and went, that's not over here. Let's not let that happen this time. So right now, if I'm going to go between y equals a function and y equals a function, I want to make sure I define it right now in terms of whatever these are, a polar function. So let's change this thing. So up here, can you change this into something that's polar?
Yes.
What would it be?
R squared.
And this guy would be 8 minus r squared. Head nod if you're okay with that one. You can also check your work right here. Plug in 0 for your radius. That's 0, that's 8. You're good. So I know because I got to integrate with respect to y, sure, I got y equals and y equals, but I want to make sure I change this. Of course, get the correct order, but change it now so that my integral matches up with the rest of my variables. That's what I want. Now the rest of it, r equals, what's r equal here? And here, please. And theta equals 0. And here. We're going to double check. Y equals r equals theta equals. I have an inequality set up small to big, small to big, small to big. It looks great with one exception. What goes on the inside of that right now, please?
Function.
Whatever it is, whatever the mass density function is. So in our case, yeah, thanks for the R. You're not listening to me. That's got to go there. That's got to go there. I need to know if that makes absolute sense to you, yeah or no. You sure? Now, I told you just told you that you really should integrate this with respect to y without changing stuff first, and then plug in y. But I'll show you how to cheat at this a little bit. If this does not have that variable, you can change it whenever you want. Because right now, think about this for a second. Would this all be a constant with respect to y? That means you could pull it out. You could even pull it this way, like that r, so you could group it. If this has that variable, if this has d, whatever variable is here is in there, you can't change it. Do not change it. Avoid change at all costs. You can't do that. But if your function does not have this variable in it, you can change it whenever you want. You just have to know what you're doing. Does that make sense? Do you understand when you can change it and when you can't change it? If this variable is anywhere in that function, you can't. You have to integrate first. If this variable is not in that function, you can change it right now. So let's do that just so I can show you how this method works. I've already shown you you don't have to change it. Now I'm going to show you how you can change it if the variable is not related to your d, whatever the R3 symbol is. Does that make sense to you? So let's change this here. I love changing stuff that's square root of x squared plus I don't care whatever squared. What's that going to give you? R. Yeah. R. I watched Pirates of the Caribbean this weekend, so it was my birthday. I get to do what I want. Pirates of the Caribbean. Boom. R. No? Huh?
Saturday?
Saturday was my birthday. It was, for real.
My wife's birthday.
I turned like 27, so. In my dreams. I don't know if I'd want to be there. Let's say what?
Like the 10th time?
10. You shall not! Oh, I've used that one already. The question was, am I in my 40s?
Yeah.
I'm 83. I aged really well. Strict diet of quinoa and steroids. Lots. And that's a lie. That's a lie. I'm just joking. Don't take steroids. They do weird things. Ask my uncle. He was Mr. America. Look him up. Gary Leonard. For real.
Mr. America?
Although he was, for real. Taught me everything I know about not taking steroids. Yeah, no, he's massive. Like he was. He's still in great shape. I don't actually think he took steroids, but around the time in the '80s, a lot of bodybuilders did.
Yeah.
It's what they did. They took steroids to get to recover, and they'd also take uppers to work out as hard as they could, and then just not good, man, not good. So let's do our triple integral, the complete setup. You can change this if this variable's not in there. So we're sorry, we're back on track and sidetracked. 0 to 2 pi. I don't ever do that, do I? 0 to 2. This don't change. This is still r squared to 8 minus r squared. But this you can change. This is now r dy. We'll do that first. Then we won't forget our r, dr d theta. This is your chance to practice. I want you to do that integral. Go for it. You know I was joking about the steroids thing, right? Okay, that was a joke. Maybe it was a joke in poor taste, but it was a joke. Goodness.
No, it does.
Not a little bit. Did you make it that far? Did you integrate with respect to y and get at least a y up there? And plug in for the y? Okay, we can do that. Just don't forget your already thetas. That's important. So here we have our you can see it too. You can see the outside function minus the inside function. That's taking the subtraction of the volumes there. Maybe simplify a little bit before we continue. Looks like we have (8r squared) (2r to the fourth). I believe I did it right. Double check me though. Did you guys get the same thing?
Yeah.
Now we still haven't even integrated with respect to r yet, but we have cleared out that r, that's r squared, 8r squared minus 2r to the fourth. And then we do the dr d theta. And it's pretty basic from here. Let's see, plug in 2. Looks like 64 thirds minus 64 fifths d theta. Like our parallel zero. Listen, you're always welcome to combine like terms before you integrate. That's a really good idea. I think. Double check my work though. 64 fifteenths. No. 128. 128. Sorry. Fraction button on a calculator, man. Best thing ever. So cool. If we integrate a constant with respect to theta, we get theta. We plug this in. Theta equals 0 to 2 pi. Looks like we get 256 pi over 15. I think that's pretty much it. We're able to get it. Now what is it? What's that represent? Mass. Mass of what? Come on, help me out. Mass of what? Mass of the thing. What thing?
The mass of the region defined.
Region between them. Some 3D thing has a mass. The mass density is given by that. We just found the mass of this. What would that be? Frisbee disc sort of thing? With a weird bottom on it. That's what that is. We just found the mass of that thing that hard to picture. But that's what we did. And none of you are okay on that idea. You sure? You're sure? Or is that just an ice cream cone? Kind of like an ice cream cone. Yeah. Yeah, it's all that if you draw it to really see. But that's the idea. That's what we're doing now. I want you to recall something here for a second. Do you remember how we had this little sidetrack? We said, wait a minute. What if you don't have a function in there? What if you have just 1 and you integrate a double integral over r with respect to the area times 1 basically just gives you the area of the region? Do you remember doing that? Well, the reason was it was volume is the basic idea. Length times width times height. What if your height was 1? Well, then you just get length times width. But that's exactly what area is. And that's a really basic explanation for how this works. I proved it a while back. We talked about it a while back. Well, now let's go further. Can we do the same idea with volume? If a double integral over a region of 1 gives us area, then a triple integral over a 3-dimensional region with a height of 1 with respect to volume is going to also give us volume. This is a different way to find volume, which is a really interesting thought because we already had double integrals, right? Double integrals over surfaces give us volume under the surface. Well, if we can define that region in three space, and we just do a triple integral over the region, we also get the same volume. It's just a different way to find volume, a really interesting way. So we can do that as well. Let's try just two of these. We're going to focus really on the setup on these guys. We'll do that. We'll come back. We'll talk about center of mass. We talked about a little bit of that in 14.4. Talk about center of mass, and that should pretty much wrap this section up. Tell you what, let's take a break now. We'll come back and talk about how we apply this to some of our regions. Math. So this is a little bit later. Right now we got to practice that last concept I put on the board over here saying, hey, you know what? Just like we can find area of a region with a double integral, we can find volume of a 3D region with a triple integral. Just the kind of little mathematical manipulation that we do. So we're going to find the volume of this region right there. This is not a region between two functions, so this is a little bit nicer. You don't have to find intersections. All we have to do is determine R3 simple, then the R on whatever plane we have, and set up a triple integral. It's, in fact, even easier than that, because I don't have a mass density function. I'm not asking about the mass. We're switching gears. We're asking about the volume right now. So, number one thing, let's check it out. We do R3 simple. What would you choose as R3 simple? There's actually two choices here. What would you choose? You could choose X. Why? Why could you choose X and be okay?
You already actually options.
And I like Z. I like the zero. I like that. X gets a little bit funky because I have X and X and X. Does that make sense? That's a little hard to deal with. Might not be the best choice. How about Y simple? No, because there's only one Y. That would not be a good choice. You'd have to break that up into two different functions to do it. I don't want to do that. So what's the correct choice? Z simple. So definitely Z simple. Keeps our region nice. No ambiguities here. Z simple is the way to go. Which means I'm going to have to mash Z between two functions of Z equals. I already know the small one. What's the small one?
Zero.
What's the large one?
The other ones.
The other one. Yes, very good. What other one? That one. Well, there's only two functions that have Z's in it. That's what makes nice. You limit your choices. So from here, I know that Z equals 4 minus X. That's going to be the upper function. Again, if you didn't know that, if you couldn't see it, and zero is nice because it kind of makes the choice for you. If you didn't know that, what would you be doing right now before you set this up? What would you do? You got to draw the region. Now, right now, speaking of the region, if we chose Z simple, the region, everybody's going to be on what coordinate plane?
That's what?
Always draw it. So we use everything to put this on the XY plane. Z equals 0 means we're on the XY plane. X equals 0. That's the Y-axis. We label all of this stuff. Hey, how about this one? Is this going to be relevant for the XY plane?
Yes.
Everything with X's and Y's in it is relevant. Even if it gives us just constants, it's relevant. So if I have X plus Z equals 4 and I'm on the XY plane, what's the value of Z on the XY plane?
4. 0.
On the XY plane. This gives us another line. So I know right now, that I can't go any further than between 0 and 4 along the x-axis. That's important. I know I can't go outside that. So probably if I do dx last, I'm going between 0 and 4. Almost guarantee it. But we're going to draw the rest of it. There's one more to draw. Oh, hey, that's kind of nice. This is why we chose Z simple, the other reason, because that's a really nice, simple shape on the XY plane. That's a cylinder along the Z axis. Has a nice shape on the XY plane. What is that shape? Yeah, it's a parabola, shifted. Oh dear. Do you know how to draw that?
Yeah.
That's a type 2 parabola. It's depending on y. So it's a parabola that's opening towards the negative negative x-axis, shifted positive 4 along the x-axis. That parabola looks like this. You guys okay with that one? You sure? Now, might want to know where that intersects the y-axis. How would you figure that out? Yeah, if you know that x is 0, and you know that these things are going to intersect, so x equals 4 minus y squared, you go, well, where's that intersect the x equals 0? 0 equals 4 minus y squared, y would equal plus or minus 2. So down here, negative 2, up here, positive 2. Should have answered okay with that one. That's our region. Now, did this play a big part in defining our region? Well, no, not really. But you put it on the graph because it might. If this had been an upward opening parabola, it certainly would have. Does that make sense? Put everything on there, and then you look at the region that's bound by whatever functions you just put on your coordinate plane. Right now, this is our region right there. Now, here's my next question. What point would you plug in to determine whether this is right? Would you plug in the point 0, 0? No, not so much. I wouldn't want to do that. What I would plug in is something like 0, 1 and see if that works. If I plug in 0, 1, well, x is just 1. I get 3, I get 0. I know that that's an appropriate orientation there. Head nod if you're okay with that one. Okay, so I guess you plug in 0. So would it work there also? You have that cylinder going up. So anything else? Usually you want to pick something inside of that region. That goes without fail if you pick something inside of the region. So I know I'm going to be set my triple integral with dz first. You tell me, what's the appropriate choice for the R2 symbol? Would you want to go along the y-axis first or along the x-axis first? What would you want to do? If I did the y, do you remember how this is given by one function? If I did the y, if I did that first, how would you go between one function? Well, you'd have to break it up. You'd have to solve this for y equals square root from here. Y would equal square root of 4 minus x. Does that make sense? Let's see, have I done that right? Subtract, square root. You have to do that, plus or minus. You could do it. Is that going to be fun? No. Maybe that's not such a good choice. Also, I'd have to be plugging in two functions. I also don't want to do that. So when we start breaking up functions to go along a certain direction, try choosing the other direction, try choosing the other axis, and see if it goes better. Does that make sense to you? Yeah. Okay, so here, yeah, I really don't want to do that. I really don't want to go along dy first. I'd like to go along dx. I'd like to go along to x first, which means that I have this function x equals 0. I've got this function x equals 4 minus y squared. That's a much nicer way to go. Does that make sense to you?
Yeah.
Yes.
You sure? So I had z simple, cool. Mash z between two functions. I got it. Go across the 3D space. Then I'm going to go along the x direction. That means I've got to mash x between two functions of x equals. What's the first one? Come on, help me out. What's the first one as I'm going through the region? What do I get to?
0.
That's why I put everything on the graph. 0. I don't make it to the x equals 4. I'm bound by this one. I'm bound by, when I reach the far end of my region, 4 minus y squared every single time. Okay, truly, show of hands if you feel okay with that. Now I also have to go between constants for my y. And if you look at it, along my y-axis, I hit the region at -2 and a maximum of +2. So anytime we're setting a region, R3 simple first, we typically pick Z simple if we can. It makes our regions kind of nice. If it's given to you like all Y equals or X equals, then fine. Of course, pick those Y or X simple. After that, we draw a region on whatever coordinate plane does not involve your R3 simple variable. No problem. Draw everything that you can. Look at the region that's bound between the curves, and then set up a really nice R2 simple. Something, hopefully, that goes between 0 and a single function. That's what you want. Don't start going in directions that force you to break up functions into 2 different functions. That's horrible. Because if I did this first, I'd go between 2 kind of nasty functions, both of which have square roots. That sucks. Don't do stuff like that. Does that make sense? So keep it as simple as possible. That's why they call it Z simple, right? That's not what they call it. But it does make it nice if you can go between 0 and 1 function. That keeps it really nice. Can you do me a favor? Do yourself a favor. I'd like to see a proper setup to find the volume of that region. So let me set this up. I know that I have to do dx, dy, dz, but it all depends on how you choose to do your simples. R3 simple said I need a dz first. After that, I went along my region in the x direction before I went along the y. So I need a dx, and then I need a dy. Do you have dz, dx, and then dy, yes or no?
Yes.
That's fantastic. Then you use what I've shown you here. We have z equals to z equals. It should have an inequality up there somewhere. X equals to x equals. You should have another inequality up there. And then y equals to y equals. Should have another inequality. It should be between functions at most, and then constants at most. That's how these things are all set up. So here, z, we got 0, 4 minus x. For x, we have 0, and then 4 minus y squared. And then for y, we have negative 2 to 2. Now, next question for you guys. What goes there? 1. Nothing. Because that's the whole nature of this volume. If I take if I do a triple integral over a region with a height of 1 in 4 dimensions, what we're getting is this 4-dimensional thing that's numerically, not unit, numerically equal to the volume of that 3D region. That's what we're doing, just like the area over a double integral. Same thing. Now, could you do that if I asked you to? What would your first step be? With respect to, you're just going to get a z. Then you're going to plug in stuff for z, integrate with respect to x. You're going to plug in stuff for x, integrate with respect to y. You're going to plug in stuff for y. Bless you. I really don't want to go through the whole motions of doing this triple integral. Would you guys be okay if setup was the most important thing. Would you be okay if I just give you the answer and you try it later? The answer on this thing, if you want to check it later, you know what to do. Z, plug in for z. X, plug in for x. Y, plug in numbers. You're going to get 128 over 5. Here's the thing I want to make absolutely clear. Do you feel confident on setting up a triple integral right now? The steps. What's your first step?
R3 simple.
R3 simple. X, Y, or Z. Pick the best choice. After that, you do what? A region on a coordinate plane. Then you draw that region and you determine whether it's polar, circles and stuff, or non-polar, rectangular equations. And you choose the appropriate direction, either along the x or along the y. You set up your triple integral, and then it's all easier after that. I do have one more example. I don't really think I want to do it. You guys seem to be getting this really well. Is it okay? Do you guys want to skip that one and go on to this stuff, or do you need another example? You feel okay with that? Okay, so let's move on. The last thing, we talked about this in 14.4. We did it, though, with planes, things that were like two-dimensional. Now, regions on planes. Now we're going to talk about three-dimensional. So we still can find the center of mass of a three-dimensional region. We've already done the first part. Actually, that's exactly what we've been doing this whole entire time. We said, hey, what's a triple integral? We could think about it as the mass of a 3D region if we're given a mass density function. That's literally what we've been doing the entire time. The rest of it says, well, the first moments of mass look really similar. It's just I don't have double integrals, I have triple integrals. I'm not going about an axis, I'm going about a plane now. And you see the pattern. If I want to go about the YZ plane, I'm going to call that the first moment about the YZ plane. And what we learned about last time in 14.4 was that all of the variables are opposite of what you have here. So if I'm going about the YZ plane, look at the board so you don't get confused in your head. This is literally just the same thing as mass. Do you guys see it? If I want to find the first moment of mass, I need to compare that to how far away the mass density is along the axis perpendicular to the plane. So perpendicular to the YZ plane, that's x. That's an x direction. Perpendicular to the XZ plane, that's a y direction. Perpendicular to the XY plane, that's a z direction. They look very, very similar to stuff we've done at 14.4. And then if you remember the center mass idea was, hey, you take the first moment of mass, divide by the total mass of that region, and you get this kind of average along the x-axis. Same thing for the y-axis, same thing for the z-axis. And if you put it all together, you get the center mass of a 3D region. That's it. Have we done this before? Oh yeah, this is what triple integrals are. We've done that a ton. This is exactly the same thing, exactly the same setup. You just tack on an x, a y, and a z, and it gives you the x, the y, and the z coordinates if you divide by mass. And that gives you the center mass. That's typically how these things are used, is find center mass of a 3D region. We're not going to do any examples of this in this section. But in the next section, you're going to get a shot at doing this. We're going to find the center mass with some triple integrals. We also have, like on top of this stuff, we also had second moments. You guys remember talking about second moments of inertia, all the inertia stuff? We also have that. It gets a little more hectic, but I'm going to talk about the second moments. Of inertia, and we'll do one pretty much just setup problem and go through it. So, second moments of inertia. What the second moment about the x-axis? That's basically saying how hard is it to get this 3D thing moving about the x-axis? The larger the number, the harder it is to get to move. Same thing with respect to the y-axis and the z-axis. We also had this idea that if we're talking about the x-axis, it's using the two different variables to compare this. You're still going to have a mass density function. But inside of our triple integral that we create here, leave yourself some space. I'm not going to go through like a rigorous proof or anything for this. I just want to get the idea in your head. If I am talking about this 3D mass that's away from the x-axis, and I'm trying to say how hard is it to get this 3D mass to move about the x-axis, to get it started, that's an inertia concept. Well, I have two measurements. I've got how far it's away from the x-axis in the x direction and in the y direction. Does that make sense? I've got two of them. If you compare that to the moments of inertia for 14.4, there was only one other variable along there, okay? But here we got two. We're going to have the other two variables not on this axis. So, and oh, by the way, and the moments of inertia from 14.4, they were all squared. They're squared here also. That's how you find the second moments of inertia. We're going to do one kind of quick example about how to do this, and then we'll be good to go. If you need a refresher, go back and look at the 14.4 stuff about moments of inertia. You're going to see a lot of similarities between first moments of mass, where the stuff comes from, how we get this, where the center mass is, and what the moments of inertia are. They look very, very similar. Are they super hard to do? Well, there's two things that make these things difficult. One is the setup of the region, but you guys know how to do that, right? Set up the region. That's the hardest part. The second hard part is when you start tacking stuff on in here, this can make your stuff freaking crazy, okay? So you start doing this, and then you have a mass density function. This can get some nasty, nasty triple integrals in there. Not because the region's hard, but because you're starting to integrate with lots of different variables. And you're plugging in and you're distributing like crazy. Does that make sense? So that can make it difficult. Let's try one example. I'm going to give you a mass density function. We're going to find the moment of inertia about the y-axis for this region I'm going to create for you. So I'm giving you a mass density function that's related to this 3D region. This thing's going to create a region for us. What we're looking for is how hard is it to get this region started about the y-axis, given that it has that mass density function. Does that make sense? The mass is increasing as we go along the z-axis. That's what that says to us. Okay, well, it's just a setup. Man, it's just a setup of a triple integral. What's the first thing you do with the setup on a triple integral every single time? What do you do? Let's set up R3 simple. So write that down. Listen, I don't want to make this harder than it is. Do you guys recognize that this is exactly the same concept? You just have a formula, you got to add some extra variables onto there.
Yeah.
It's the same thing. So R3 simple, oh man, you got two choices here. Two choices. What two choices could you do? You could do all three, really, if you wanted to. What could you do?
Y is Z.
Z simple, you could do Y simple, you could even do X, well, X simple would get a little funky because you have three of them. But it's probably between Z simple and Y simple. What's the better choice between Z simple and Y? Why is Z simple? You're right, but why?
Zero.
I love the zero. Love the zero, and that keeps our region kind of easy to draw on the XY plane. And we can draw those things really nicely. So let's pick Z simple. That means that Z is going to get matched between two functions of Z equals, you tell me what the smaller one is. What's the larger one? It's literally given to you. Use that. That's so nice. So if we're doing Z simple, you all need to tell me what is the region, what coordinate plane is the region on? We should draw this every single time. if we draw that, we go, okay, well, sure. Oh man, is that relevant? No, that's telling us that we're on the xy plane. Is this relevant? Yes, because on the xy plane, z equals x becomes 0 equals x. Okay, so that's x equals 0. That's giving us a y-axis. That's already helping us just a little bit there. At least it's giving us something. Next up, so that's one. How about y equals x? Is that relevant? Oh, that's certainly relevant. That's literally a line on the xy plane. So let's draw that line. And then we have this y equals x squared, also relevant. So 1, 2, 3 lines that we get out of this thing. Y equals x squared, well, that's... Over here is not relevant. It's not creating any additional region for us on the left-hand side. So just focus on quadrant 1 right now. And now that you're okay with that one. So our region is this guy. We got y equals x and y equals x squared. Man, it helps to draw those regions. It literally shows you everything you want. Now, what would you do? We've already done z simple. The next thing I need to do is pick an r2 simple. So somewhere across this region, either along the y or along the x. What's the appropriate choice? Would you go dx along the x or along the y? What would you do? Why? Why would you go along? You're right, but why would you go along the y? I don't know. It's already there, yeah. If I had to solve it for x, it'd be kind of annoying because I have some square roots. I have to plug in some square roots. Do you want to do that? Well, I don't either. You could do it. You could go this way, but you'd have to solve for x. This one's already solved for x, kind of universal, but this one would suck. You got that plus and minus square root of y. You'd get positive square root of y, but you'd have to plug it in square roots. Do you guys want to plug in square roots? Then stick a... Yes, I love square roots. I love 1/2 over 1/2. X to the... Oh, sorry, 3/2 over... Whatever it is. I don't want to do that because I don't want to have to solve for x because that's annoying. So for the R2 simple, let's go dy first. Let's go between two functions of y. That's what that means. So our two functions of y, what's the smaller of those two, please? Larger? Now, if I do that, if I go along the region R2 simple between two functions of y, that leaves me with my constants along the x. So I need x to be between constants. What constants are? I don't see any constants. What constants are they?
0 and 2.
0, sure, 0. But what other number? What is it?
1.
Yeah, don't guess at it though. If it's not obvious, how do you find what that point is? Set the functions equal. So we go, okay, well, if I set these things equal, x squared minus x equals 0, set them equal, subtract x minus 1, I know that x equals 0 and x equals 1. That gives me my constants. If that's 1, 1, which it is, then I get 0 to 1. And now if you're okay with that one. What I want is a perfect setup of your triple integral. Again, we're finding the moment of inertia, second moment of inertia about the y-axis. So you look at the formula, set up a perfect triple integral for me. That's what I want. So z simple dz first between 0 and x. R2 simple was along the y, so dy y equals between x squared and x. Did you make it that far so far? Yes, yes? Last one. Constants. Our x is our last one. Constants from x equals 0 to x equals 1. Hey, that's the region. By the way, if I left it right here, and integrated from this right now, what would it give me? Yeah, that's right. Give me the volume of the region. If I did this and integrated with that, what would it give me? That's right. That's the mass of the region. And now to find the second moment of inertia about the y-axis, I need to have the other two variables squared and added. So I need to have x squared plus z squared in there as well to find the second moment. That's the correct setup. I need to know if you all got that. Show of hands if you did. That's fantastic. Again, I'm going to leave it to you. This one's kind of an easy one. What's the first thing you're doing on this problem? Before you integrate, don't do a U sub here. Don't waste your time doing a U sub. Okay, please don't do that. Distribute. Don't do U subs with power ones. That's like a universal. That's like a face punch your test. Okay, don't do that. If you don't have powers here, do not do U subs because it's easier to just distribute that and do basic integration. Does that make sense? So do I need to do it? Distribute this. That's x squared z. This is x to the third. Integrate with respect to z. You're going to get a 1/2. You're going to get 1/3 z squared, z to the third, blah, blah, blah. Plug in for z, integrate with respect to y. Plug in for y, integrate with respect to x. Plug in some constants and get 1/56. That's a measurement of how hard it is to get that volume started moving around the x-axis, y-axis. That's what that number is. Larger numbers, harder it is to move. I need to know if I explained regions on triple integrals well enough for you. Okay, because the next section, section 14.7, we start crushing this stuff, and I start making it a little different. What if our regions are cylinders? Remember, regions are 3D now, right? So what if our regions are not between planes, cut up in planes? What if they're on cylinders, or cones, or spheres? We're going to have stuff very akin to polar coordinates. Only now it's in 3D. Cylindrical and spherical. That's where we're going with it. Does it make sense?